every ancient civilization had access to something modern researchers do not: first-hand knowledge of its own world. They knew why a monument was built, how a city functioned, what symbols meant, and which traditions guided their decisions. Then, over centuries, that knowledge disappeared. The structures remained, but the explanations did not. Today, archaeologists often stand inside buildings that are thousands of years old and can describe their dimensions with incredible accuracy, yet still debate their true purpose. A chamber survives, but its meaning is uncertain. A city survives, but its story is incomplete. The ancient world is filled with places where physical evidence outlasted human memory. And that is why so many mysteries remain unsolved. Lissos, a forgotten ancient city hidden on the remote southern coast of Crete, remains one of the most intriguing archaeological mysteries in the Mediterranean. Surrounded by steep mountains and accessible even today mainly by boat or long hiking trails, Lissos should never have become a prosperous urban centre. Yet archaeological evidence shows that this isolated settlement flourished for centuries as a religious, medical, and commercial hub. More than 2,000 years later, its ruins still raise questions about lost engineering knowledge, vanished medical practices, and sophisticated technologies that remain only partially understood. The ancient city lies within a narrow valley facing the Libyan Sea, approximately 70 kilometers southwest of modern Chania. Historical sources identify Lissos as an important city-state during the Hellenistic period and later a thriving center under Roman rule. The site was first described by European travelers during the 19th century, while systematic archaeological investigations conducted throughout the 20th century revealed temples, residential buildings, water systems, baths, cemeteries, inscriptions, and one of the most important healing sanctuaries in ancient Crete. Yet every excavation seemed to uncover new questions rather than provide answers. The first mystery begins with the city's location itself. Ancient engineers selected one of the most geographically challenging locations imaginable. Steep limestone mountains rise immediately behind the settlement, while the coastline offers only limited flatland for construction. Unlike major Mediterranean cities such as Alexandria, Ephesus, or Carthage, Lissos lacked vast agricultural plains capable of supporting large populations. Yet archaeological evidence suggests that the city remained occupied and economically active for several centuries. Researchers continue to debate how thousands of residents sustained themselves in such a restricted environment. The logistical challenge becomes even more remarkable when considering the transportation of construction materials. Large stone blocks, columns, roofing materials, and imported goods had to reach a settlement isolated by rugged terrain. Similar engineering questions are often raised at Machu Picchu in Peru, where builders transported massive stones across mountainous landscapes. Although the scale differs greatly, the underlying challenge remains surprisingly similar. How did ancient societies organize complex construction projects in locations where transportation appears extraordinarily difficult? The second mystery concerns water. Southern Crete experiences long dry seasons and receives significantly less rainfall than many parts of northern Greece. Yet excavations at Lissos revealed sophisticated hydraulic infrastructure, including cisterns, reservoirs, channels, and public baths. Roman baths alone required substantial and reliable water supplies. Researchers estimate that public bath complexes in Roman cities often consumed thousands of litres of water daily. Maintaining such facilities in an isolated coastal valley would have required precise water management strategies. Some scholars suggest that engineers captured seasonal runoff from surrounding mountains and stored it in large reservoirs. Others propose the existence of carefully managed spring systems that have not yet been fully identified. Modern surveys have mapped portions of the hydraulic network, but the complete system remains unknown. The mystery resembles questions surrounding Petra in Jordan, where ancient Nabatean engineers transformed an arid environment into a functioning urban centre through advanced water management techniques. In both cases, surviving structures demonstrate engineering success, while the full operational knowledge behind that success remains incomplete. The greatest mystery of Lissos, however, revolves around its famous Sanctuary of Asklepios. This sanctuary transformed the city into one of the most important healing centres in ancient Crete. Archaeologists discovered inscriptions, statues, architectural remains, and offerings dedicated to Asklepios, the Greek god of medicine. Historical evidence indicates that patients travelled from distant parts of Crete seeking treatment within the sanctuary. This immediately raises a fascinating question. What made the healing centre of Lissos so special that people were willing to undertake difficult journeys across mountains and coastlines to reach it? The sanctuary functioned during a period when medicine existed in a unique intersection between religion and empirical observation. Ancient Greek physicians associated with the Asclepian sanctuaries often combined spiritual rituals with practical treatments. However, the specific methods used at Lissos remain largely unknown. Inscriptions confirm that patients visited the sanctuary, but detailed records of treatments have not survived. As a result, researchers must reconstruct its medical practices indirectly through archaeology in comparison with better documented healing centres. One possibility involves the local environment itself. The mountains surrounding Lissos support a remarkable diversity of medicinal plants. Crete contains more than 1,800 plant species, including numerous endemic varieties found nowhere else on Earth. Some botanists have suggested that ancient healers may have possessed extensive knowledge of local herbs with therapeutic properties. Such expertise could have contributed significantly to the sanctuary's reputation, yet almost none of this knowledge was recorded in sufficient detail to survive. If generations of healers developed specialized treatments based on local botanical resources, much of that expertise disappeared with the decline of the sanctuary. Another possibility involves mineral-rich water sources. Across the ancient world, healing sanctuaries frequently developed near springs believed to possess therapeutic qualities. Similar patterns appear at Epidaurus in mainland Greece, the most famous sanctuary of Asklepios, where water played an important role in ritual purification and treatment practices. Some researchers suspect that springs near Lissos may have contributed to its medical reputation. However, no definitive scientific evidence has yet explained whether the water possessed measurable therapeutic characteristics, or whether its significance was primarily cultural and religious. The sanctuary also presents architectural mysteries. Excavated remains reveal a carefully planned complex integrated into the landscape. Ancient builders selected locations, orientations, and spatial arrangements that may have influenced patient experiences. Modern studies of healing environments demonstrate that architecture can affect psychological well-being, stress levels, and recovery outcomes. Some scholars wonder whether ancient sanctuary designers intuitively understood principles that modern medicine now studies scientifically. The question remains impossible to answer conclusively because much of the original structure has been lost. The mystery deepens when considering the scale of the sanctuary's reputation. Archaeological evidence suggests that Lissos became known far beyond its immediate region. Such prominence required more than simple religious significance. Successful healing centers depended upon trust, reputation, and repeated positive outcomes. If the sanctuary consistently attracted visitors across generations, then something must have convinced people that treatment there worked. Whether that success derived from herbal medicine, psychological effects, environmental factors, empirical medical knowledge, or a combination of all four remains unknown. The fourth mystery concerns the vanished harbour. Historical records indicate that maritime trade connected Lissos to broader Mediterranean networks. Yet much of the ancient harbour infrastructure has disappeared. Crete occupies one of the most seismically active regions in Europe due to interactions between the African and Eurasian tectonic plates. Major earthquakes have repeatedly altered coastlines throughout the island's history. Geological studies show that some parts of Crete have experienced vertical shifts of several meters during major seismic events. Researchers suspect that portions of the ancient harbour may now lie underwater or beneath coastal sediment. If true, critical evidence regarding trade, shipbuilding, and maritime engineering may remain hidden beneath the sea. The fifth mystery involves resilience. Lissos survived earthquakes, changing political powers, economic transformations, and environmental challenges for centuries. Ancient builders constructed structures capable of enduring conditions that destroyed countless other settlements. The surviving ruins reveal practical knowledge of local geology, materials, and construction techniques. Yet the written manuals, technical instructions, and engineering calculations behind those achievements have vanished completely. Yingxu, located near modern-day Anyang in Henan Province, China, should not have existed at the level of sophistication archaeologists found. More than 3,000 years ago, this city served as the last capital of the Shang dynasty, yet buried beneath its soil were technologies, manufacturing systems, and administrative capabilities that in some cases rivaled or exceeded those of many contemporary civilizations. The greatest mystery is not that Yingxu existed. The mystery is how a Bronze Age society developed industrial-scale production, advanced metallurgy, a fully mature writing system, and a centralized network capable of managing enormous resources centuries before many comparable societies elsewhere. The rediscovery of Yingxu began in 1899 when scholar Wang Yirong noticed strange symbols carved onto so-called dragon bones sold in Chinese medicine shops. These bones were later identified as ancient oracle bones containing the earliest known form of Chinese writing. Systematic excavations began in 1928 under archaeologist Li Ji of the Institute of History and Philology. Over the following decades, archaeologists uncovered palace foundations, royal tombs, workshops, sacrificial pits, and more than 150,000 oracle bone fragments. What emerged was not merely a lost city but evidence of one of the most technologically advanced civilizations of the Late Bronze Age. The first and perhaps greatest mystery of Yingxu is its bronze casting technology. Bronze production was common throughout the ancient world, but the scale and complexity achieved at Yingxu remain astonishing. During the Shang dynasty, craftsmen produced massive ritual vessels weighing hundreds of kilograms while maintaining extraordinary decorative precision. Some vessels display intricate patterns covering every surface, including deep relief designs that would challenge even experienced modern metal workers. What makes this achievement particularly mysterious is the casting method itself. Unlike ancient Egypt, Mesopotamia, and later Greece, which primarily employed variations of lost wax casting, Shang craftsmen relied on a technique known as piece mold casting. This process required artisans to first create a clay model, then build multiple molds around it, remove the molds, carve detailed decorations into the mold surfaces, reassemble them perfectly, and finally pour molten bronze into the cavity. The challenge becomes clear when examining the physics involved. Bronze melts at temperatures exceeding 950 degrees Celsius. Large vessels required enormous quantities of molten metal to be poured rapidly and evenly. Any slight misalignment between mold sections could ruin the entire object. Thermal expansion, shrinkage during cooling, trapped gases, and uneven metal flow all presented serious engineering obstacles. Yet archaeological evidence suggests Shang workshops consistently achieved remarkable success. One famous example is the Simu Ding discovered near Yingxu in 1939. Weighing approximately 832 kilograms, it remains the heaviest ancient bronze vessel ever found in China. Producing such an object would have required more than 1 ton of molten metal and an exceptionally stable casting environment. Even modern engineers debate exactly how Shang craftsmen controlled temperature gradients and metal distribution during the casting process. Experimental archaeology has successfully replicated smaller objects, but many questions remain regarding the production of the largest vessels. Comparisons with other Bronze Age civilizations only deepen the mystery. During the 13th century BC, when Yingxu flourished, many Mediterranean societies produced bronze objects measured in kilograms. The largest Shang ritual vessels often exceeded those weights by an order of magnitude while incorporating significantly more complex decorative programs. The technological gap is difficult to explain solely through gradual development. The second mystery concerns the enormous supply chain required to sustain this bronze industry. Chemical analyses of Shang bronzes reveal mixtures of copper, tin, and lead in carefully controlled proportions. Copper isotopic studies suggest that ores originated from multiple mining regions located hundreds of kilometers from Yingxu. Maintaining continuous access to these resources would have required organized extraction, transportation, storage, and distribution systems. Archaeologists estimate that thousands of tons of metal were consumed throughout the Shang period. Such production implies the existence of large mining operations, skilled labor forces, and administrative oversight. Yet the full extent of this network remains unknown. Many of the mines that supplied Yingxu have not been conclusively identified, creating a significant gap in our understanding of how the Shang economy functioned. The third mystery involves the sudden appearance of a mature writing system. The oracle bone inscriptions discovered at Yingxu represent the earliest substantial corpus of Chinese writing ever found. More than 150,000 fragments have been recovered containing approximately 5,000 distinct characters. Of these, scholars have deciphered roughly 1/3 with reasonable confidence. The problem is that the system already appears highly developed. The inscriptions include phonetic components, semantic elements, grammatical structures, personal names, military records, agricultural reports, astronomical observations, and ritual instructions. Writing systems generally evolve through long transitional phases, leaving behind simpler intermediate forms. At Yingxu, however, the script emerges in the archaeological record already functioning as a sophisticated administrative tool. This raises a profound question. Where are the earlier stages? A fully mature writing system does not appear overnight. Many researchers believe that centuries of written tradition must have preceded the inscriptions found at Yingxu, yet definitive evidence for those earlier phases remains elusive. The fourth mystery centers on the oracle bone divination system itself. To modern observers, oracle bone rituals may appear purely religious. In reality, they constituted one of the most organized information management systems of the ancient world. Shang diviners drilled precise pits into turtle shells or animal bones and applied heat until cracks formed. Questions regarding warfare, harvests, weather, royal births, hunting expeditions, and political decisions were then interpreted from the resulting patterns. What is remarkable is the degree of standardization. The placement of pits, the methods of heating, the recording of questions, and the documentation of outcomes followed consistent procedures. Thousands of inscriptions effectively created a database spanning generations. Some historians compare this system to an early form of bureaucratic record-keeping, preserving information on an unprecedented scale for the Bronze Age. The fifth mystery involves astronomy. Numerous oracle bone inscriptions record eclipses, planetary movements, lunar phases, and unusual celestial events. These observations demonstrate that Shang scholars tracked astronomical cycles with surprising accuracy. Certain inscriptions correspond closely with eclipses that modern astronomers can calculate retrospectively. Such precision required systematic observation over long periods, yet archaeologists have found little evidence for large observatory complexes comparable to those known from later civilizations. How Shang astronomers accumulated and preserved their knowledge remains poorly understood. The sixth mystery emerged dramatically in 1976 with the excavation of the tomb of Fu Hao. Unlike most royal Shang burials, which had been looted centuries earlier, Fu Hao's tomb remained largely intact. Archaeologists uncovered more than 1,900 artifacts, including nearly 500 bronze objects, hundreds of jade pieces, ivory carvings, stone tools, weapons, and thousands of cowrie shells used as currency. Oracle bone inscriptions identify Fu Hao as both a queen and a military commander. Records suggest she led campaigns involving thousands of soldiers. If these texts are interpreted correctly, the Shang state possessed military capabilities far larger and more sophisticated than previously assumed. Yet many details regarding recruitment, logistics, command structures, and battlefield organization remain unknown. What do you think is the greatest mystery of Yingzhou? The giant bronze vessels, the lost origins of Chinese writing, or the knowledge that vanished with the Shang dynasty? Meninx, located on the southeastern coast of Jerba Island in modern-day Tunisia, was once one of the wealthiest cities in the Roman world. Yet its greatest mystery was not a palace, a temple, or a fortress. It was a technology. For centuries, Meninx produced one of the most valuable substances on Earth, Tyrian purple, a dye so expensive that Roman emperors restricted its use to the highest ranks of society. Even today, despite modern chemistry, researchers still debate how ancient craftsmen consistently produced this extraordinary colour on an industrial scale. The ruins of Meninx remained largely buried beneath sand and agricultural land for centuries. Although travellers reported ancient remains during the 19th century, systematic archaeological investigations accelerated only during the 20th and 21st centuries. Major surveys and excavations conducted by Tunisian and German teams revealed an urban centre stretching nearly 2 kilometres along the coast. Beneath the surface lay streets, baths, workshops, warehouses, villas, and evidence of one of the largest dye production industries ever discovered in the ancient Mediterranean. The first and greatest mystery of Meninx is the technology behind Tyrian purple itself. The dye was extracted from marine snails belonging primarily to the Murex family. Ancient writers such as Pliny the Elder described aspects of the process, yet their accounts remain incomplete and often difficult to interpret. Modern chemical analysis has shown that the final pigment contains brominated indigo compounds, particularly 6,6-dibromoindigo. Producing these compounds required a remarkably complex sequence of biological, chemical, and environmental reactions. The process began with the extraction of a tiny gland from each snail. The gland contained only a small amount of precursor material. Researchers estimate that thousands, and in some cases tens of thousands, of snails were required to produce a single gram of finished dye. The glands were then subjected to controlled decomposition. During this stage, enzymes triggered chemical transformations that released precursor molecules. Exposure to oxygen, temperature changes, and sunlight caused additional reactions. At certain stages, the liquid could appear yellow, green, blue, red, and finally deep purple. This is where the mystery begins. Modern laboratory experiments have repeatedly demonstrated that slight variations in temperature, fermentation time, oxygen exposure, or sunlight can drastically alter the final colour. A difference of only a few hours may shift the result from purple to blue. Yet Meninx appears to have produced relatively standardized pigments for centuries. Archaeological evidence suggests industrial-scale production rather than occasional experimentation. How ancient workers achieved such consistency without thermometers, chemical instruments, or modern scientific theory remains poorly understood. The challenge becomes even more impressive when production scale is considered. Excavations have uncovered enormous accumulations of crushed murex shells. Some deposits contain millions of shells. Similar shell mountains are known from Phoenician centres such as Tyre and Sidon, but Meninx appears to have rivaled the largest purple dye industries in the Mediterranean. If each gram of dye required thousands of snails, then the total number processed at Meninx over centuries may have reached into the hundreds of millions. The logistics behind such an operation remain difficult to reconstruct. This leads to the second mystery: resource management. Djerba is an island, and maintaining continuous access to massive quantities of marine snails would have required extensive harvesting networks. Ancient fishermen somehow avoided collapsing local populations despite centuries of exploitation. Archaeologists still debate whether Meninx relied solely on nearby waters or whether specialized supply systems brought shells from distant regions. No written records have survived to explain how this industrial ecosystem functioned. The third mystery involves industrial organization. Modern researchers increasingly view Meninx not merely as a city but as a manufacturing center. Excavations reveal evidence of workshops distributed across large sectors of the settlement. The production process generated intense odors because decomposing snail glands release sulfur compounds. Ancient authors described purple dye facilities as among the foulest smelling industries in the Roman world. Yet Meninx successfully integrated these operations into a prosperous urban environment. How city planners balanced industrial production, residential districts, trade facilities and sanitation remains only partially understood. Another unanswered question concerns water management. Dye production required substantial quantities of water for processing, cleaning and handling materials. Yet Djerba receives limited annual rainfall, typically less than 250 millimeters in many areas. Archaeological investigations have revealed cisterns, reservoirs, and hydraulic infrastructure, but researchers still debate whether these systems alone could support large-scale industry. Some scholars suggest that groundwater extraction technologies were far more sophisticated than previously assumed. Others argue that seasonal water storage systems reached efficiencies rarely appreciated in ancient engineering. The fourth mystery concerns the city's harbour. Meninx became wealthy because it connected North Africa to the wider Roman economy. Luxury textiles coloured with Tyrian purple travelled across the Mediterranean, reaching elite markets from Italy to the Near East. However, the ancient harbour itself remains elusive. Geological studies indicate that coastlines around Djerba have changed significantly over the last 2,000 years due to sedimentation and sea level fluctuations. Portions of the harbour may now lie buried beneath sediments or submerged offshore. Remote sensing surveys have identified anomalies that could represent ancient maritime infrastructure, but a complete reconstruction remains impossible. The scale of Meninx's commercial success raises further questions. During the Roman Empire, purple garments symbolized authority, wealth, and political power. Certain shades were reserved exclusively for emperors. Historical sources indicate that purple dye could command prices comparable to precious metals. Although exact values varied across time and region, ancient records consistently portray Tyrian purple as one of the most expensive manufactured products in the world. Meninx therefore occupied a strategic position within a luxury economy whose value exceeded that of many ordinary commodities. Yet surprisingly little documentation survives regarding the administration of this industry. The fifth mystery involves scientific knowledge itself. The craftsmen of Meninx clearly understood practical chemistry, even if they lacked modern terminology. They manipulated biological materials, controlled fermentation, managed oxidation reactions, and exploited photochemical processes. Their work resembles a sophisticated laboratory operation conducted on an industrial scale. The situation invites comparison with Roman concrete, whose chemical durability still fascinates materials scientists, or the Antikythera mechanism, whose mechanical sophistication stunned modern researchers. In each case, ancient knowledge achieved results that later generations struggled to explain completely. Perhaps the most fascinating aspect of Meninx is that its technological success depended upon invisible processes. Visitors saw purple cloth. They saw wealth, they saw luxury, but the crucial transformations occurred at the molecular level. Ancient workers learned through experience how to guide reactions they could never directly observe. Long before chemistry became a science, they mastered practical methods capable of producing one of history's most coveted materials. The final mystery is the disappearance of that expertise. Meninx flourished for centuries before declining during late antiquity. Trade routes shifted, political structures changed, economic priorities evolved. Eventually the city faded, and its industrial knowledge disappeared with it. The workshops fell silent, the harbour declined, the recipes were forgotten. What remained were mountains of shells and fragments of a technology that once supplied emperors. Which mystery of Meninx fascinates you the most? Let us know your thoughts in the comments below. Hemudu is one of the oldest and most puzzling archaeological sites ever discovered in China. Located in Yuyao, Zhejiang province, near the southern edge of Hangzhou Bay, the site preserves evidence of a sophisticated society that flourished between approximately 5000 and 3300 BC. More than 7,000 years ago, while much of the world was still transitioning from hunting and gathering to settled farming, the people of Hemudu were constructing large wooden buildings, cultivating rice on a significant scale, producing lacquerware, and developing technologies that continue to challenge archaeologists today. The discovery itself was accidental. In 1973, workers involved in a water conservancy project unearthed unusual artifacts buried beneath thick layers of waterlogged soil. Archaeologists soon arrived and launched excavations that revealed one of the most important Neolithic settlements in East Asia. Over multiple excavation seasons, researchers uncovered more than 6,000 square meters of cultural deposits, thousands of artifacts, extensive wooden architecture, animal remains, and one of the largest collections of early rice remains ever found in China. What emerged was not merely a prehistoric village, but a technological puzzle that still raises questions more than 5 decades after its discovery. The first mystery concerns the astonishing wooden engineering of Hemudu. Wood is one of the least likely materials to survive for thousands of years, yet archaeologists recovered hundreds of wooden structural components, including pillars, beams, planks, tools, and architectural elements. Some of these pieces reveal the use of mortise and tenon joints, a sophisticated woodworking technique in which precisely carved projections fit into matching cavities without the need for nails or metal fasteners. The same principle would later become a defining feature of traditional Chinese architecture, including structures built thousands of years later. The mystery is not that the joints existed, but that they appeared so early. During the Hemudu period, metal tools had not yet become available. Most cutting and shaping was performed using polished stone axes, adzes, and bone implements. Modern experiments have shown that creating accurate mortise and tenon joints using stone tools is possible, but extraordinarily labour-intensive. Some joints discovered at Hemudu display levels of precision that seem surprising for a society operating entirely without metallurgy. The question remains, how did these craftsmen achieve such accuracy, and how much practical engineering knowledge has been lost? The second mystery involves the construction of large stilt house settlements in an environment that should have been difficult to inhabit. Geological studies indicate that the Hemudu region was characterized by wetlands, tidal influences, flooding, and unstable soils. Yet the inhabitants developed extensive raised wooden structures supported by deep piles driven into the ground. Excavated post holes suggest substantial buildings elevated above the surrounding terrain. This design protected residents from seasonal flooding and damp conditions. Modern engineers rely on soil analysis, geotechnical surveys, and sophisticated calculations when building on unstable ground. Hemudu builders possessed none of these technologies, yet their structures endured long enough to leave a significant archaeological record. Researchers continue to debate how these early communities assessed ground stability and selected construction sites with such effectiveness. The third mystery centers on rice agriculture. Hemudu yielded enormous quantities of rice remains, including grains, husks, leaves, and stalk fragments. Some estimates suggest that several tons of rice-related material were preserved at the site. Radiocarbon dating places many of these remains at more than 6,500 years old. Rice cultivation is often underestimated as a technological achievement. Unlike simple gathering, successful rice farming requires water management, seasonal planning, land preparation, storage systems, and knowledge accumulated across generations. Evidence from Hemudu suggests that rice was not merely collected, but systematically cultivated. The scale of production indicates an organized agricultural economy capable of supporting a substantial population. The mystery lies in how quickly this expertise developed. Compared with many contemporary Neolithic communities elsewhere in the world, Hemudu appears remarkably advanced in agricultural adaptation. Some scholars argue that the lower Yangtze region may have been one of the world's independent centers of rice domestication, but the exact process remains poorly understood. The fourth mystery concerns environmental adaptation and survival. Paleo-environmental studies indicate that sea levels and climate conditions in eastern China changed significantly throughout the Holocene period. The inhabitants of Hemudu lived in a dynamic landscape shaped by rivers, marshes, storms, and coastal influences. Despite these challenges, they maintained a stable settlement for centuries. Animal remains reveal a mixed economy involving hunting, fishing, gathering, and farming. The community exploited deer, wild boar, fish, birds, and aquatic resources while simultaneously cultivating crops. Such flexibility suggests a sophisticated understanding of local ecosystems. Yet archaeologists still struggle to explain how these populations balanced environmental risks and resource management over such long periods without written records or centralized administrative systems. The fifth mystery, and perhaps the most extraordinary of all, is the appearance of early lacquer technology. Among the discoveries at Hemudu were wooden objects coated with red lacquer. Scientific analysis confirmed that the coating originated from the sap of the lacquer tree, Toxicodendron vernicifluum. This finding stunned researchers because lacquer production is one of the most technically demanding crafts of the ancient world. Unlike simple paint, lacquer requires collecting sap from specific trees, filtering impurities, processing the material and applying it in carefully controlled layers. The curing process depends on precise humidity and temperature conditions. If conditions are too dry, the lacquer hardens improperly. If conditions are too wet, the surface can be damaged. Even traditional lacquer workshops operating thousands of years later required specialized knowledge and controlled environments. The Hemudu lacquer artifacts date to roughly 5000 BC, making them among the earliest known lacquered objects ever discovered anywhere on Earth. This pushes the history of lacquer technology back more than 7 millennia. To appreciate the significance of this achievement, consider a comparison. Ancient Egypt was still more than 2,000 years away from the construction of the Great Pyramid. Stonehenge would not begin to take shape for another 2,000 years, yet the people of Hemudu were already experimenting with a sophisticated organic coating technology that would remain important throughout Chinese history. The mystery is not simply how they discovered lacquer, but how they mastered it. Producing useful lacquer requires repeated experimentation and long-term observation. Researchers still cannot determine how many generations of trial and error preceded the lacquerware found at Hemudu, nor can they fully explain why such advanced material knowledge appeared so early in prehistory. Some archaeologists describe lacquer as one of the first examples of humanity deliberately engineering natural chemical substances to create durable manufactured materials. The sixth mystery involves the remarkable preservation of organic materials. Most Neolithic sites yield stone tools, pottery fragments, and bones because organic materials usually decay rapidly. Hemudu is different. Waterlogged conditions preserved wood, plant fibers, woven objects, and food remains that would normally disappear. This preservation provides an unusually detailed glimpse into daily life. Yet it also creates scientific challenges. Researchers continue investigating the exact environmental conditions that allowed so many fragile materials to survive for over 7,000 years. Understanding these processes has become important not only for archaeology but also for conservation science. The seventh and perhaps greatest mystery concerns disappearance. The Hemudu culture flourished for centuries and developed technologies that appear surprisingly sophisticated for its age. Then, over time, it transformed and eventually vanished from the archaeological record as a distinct cultural entity. Climate change, flooding, sea level fluctuations, migration, and cultural integration have all been proposed as explanations. None fully account for the transition. What happened to the craftsmen who mastered woodworking? What became of the communities that pioneered lacquer production? Where did their accumulated knowledge go? El Gem, known in antiquity as Thysdrus, rises from the dry plains of central Tunisia like a structure that should not exist. Standing nearly 36 meters high and measuring approximately 148 meters long by 122 meters wide, the amphitheatre of El Gem remains one of the largest Roman arenas ever built. Only the Colosseum in Rome and the amphitheatre of Capua surpassed it in size. Yet, unlike Rome, Thysdrus was not the capital of an empire. It was a provincial city on the edge of North Africa. Nearly 1,800 years after its construction during the early 3rd century AD, the monument still dominates the landscape, raising questions not only about Roman power, but also about engineering knowledge that appears remarkably advanced for its time. The ruins were never completely lost. Medieval travelers described the massive structure, and European scholars began documenting it in detail during the 18th and 19th centuries. Systematic archaeological investigations throughout the 20th century revealed underground chambers, structural foundations, circulation corridors, and construction techniques that transformed El Gem from a famous ruin into one of the most important engineering case studies of the Roman world. The first mystery begins with scale. Historians estimate that Thestros may have had a population between 20,000 and 30,000 inhabitants during its peak. Yet the amphitheatre could accommodate approximately 35,000 spectators. This means the building may have held more people than the city itself. Such a ratio is unusual even within the Roman Empire. The Colosseum in Rome served the political centre of a vast empire with more than 1 million inhabitants. El Gem, by comparison, stood in a provincial city whose wealth came primarily from olive oil production. Archaeologists continue debating why local elites invested enormous resources into a structure of such unprecedented size. Some scholars argue it was intended as a political statement demonstrating regional wealth. Others suggest it represented competition among North African cities seeking influence within the empire. No surviving inscription fully explains the decision. The second mystery concerns construction logistics. Modern calculations indicate that the amphitheatre required tens of thousands of tons of stone. The structure was built primarily from local limestone blocks cut with remarkable consistency. Unlike many Roman monuments, El Gem was constructed without relying heavily on brick or concrete for its visible exterior. Every block had to be quarried, transported, shaped, lifted, and precisely positioned. Yet there are no surviving technical manuals describing the process. Researchers estimate that thousands of workers may have participated in the project, but the organisation of labour remains largely unknown. How construction teams coordinated such a massive operation without modern machinery continues to intrigue engineers today. The third and perhaps greatest mystery is the extraordinary structural system itself. This is where El Gem becomes far more than a simple amphitheatre. It becomes a puzzle of ancient engineering. The arena has survived nearly 18 centuries despite earthquakes, warfare, stone removal, weathering, and structural damage inflicted during various historical conflicts. Large sections remained standing even after portions of the exterior were deliberately dismantled for building materials over hundreds of years. What makes this survival remarkable is the apparent simplicity of the design. Roman builders possessed no structural analysis software, no finite element modelling, no reinforced concrete, and no modern understanding of stress distribution. Yet the amphitheatre behaves like a carefully optimised load-bearing machine. The entire structure consists of a series of concentric rings connected through radial walls and stacked arcades. Loads from the upper levels are transferred downward through arches, columns, and vaults before reaching the foundations. Every arch redirects compressive forces into neighbouring elements, reducing localised stress concentrations. Modern engineers recognise this principle, but the mystery lies in how accurately Roman builders applied it. The dimensions of the arches are not random. The spacing between supporting elements follows patterns that maximize stability while minimizing material use. Some researchers have compared Roman amphitheatres to modern shell structures because both achieve remarkable strength through geometry rather than mass alone. The comparison becomes even more striking when examining structural efficiency. The Great Pyramid of Giza survives largely because of its enormous volume and weight. El Gem survives through balance. It uses far less material relative to its enclosed space while maintaining long-term stability. This required a sophisticated understanding of force transfer that Roman engineers never fully documented. Archaeologists can measure the results, but the exact methods used to determine proportions remain uncertain. Even more intriguing is the absence of significant asymmetrical settlement. Structures of this scale normally experience uneven foundation movement over centuries, yet much of El Gem maintains remarkable alignment. Geological studies suggest that builders carefully selected and prepared the site before construction began. How they evaluated soil conditions without modern geotechnical equipment remains unclear. Similar questions surround Roman bridges, aqueducts, and harbours. where empirical knowledge often produced results comparable to those achieved through modern calculations. Another mystery involves crowd management. Modern stadium designers use computer simulations to analyze pedestrian movement and emergency evacuation scenarios. LGEM achieved similar objectives nearly 2,000 years earlier. Its network of entrances, corridors, stairways, and seating sectors allowed tens of thousands of spectators to enter and exit efficiently. The design reduced congestion while directing visitors toward assigned seating areas. Studies of Roman amphitheatres suggest that crowd circulation was integrated into the structure from the earliest planning stages. Yet the mathematical principles behind these layouts remain unknown. Beneath the arena lies another technological puzzle. Excavations revealed underground chambers and passageways used to house animals, equipment, and performers before events. These spaces form the operational heart of the amphitheatre. Evidence suggests that mechanical lifting devices may have transported animals and scenery to the arena floor. Similar systems existed in the Colosseum, where elevators powered by human labour raised cages through trapdoors. However, much of the original machinery at LGEM disappeared long ago. Archaeologists can identify structural traces, but reconstructing the exact mechanisms remains difficult. The surviving architecture implies a level of mechanical planning far beyond what most people associate with the ancient world. The arena also raises questions about Roman acoustic knowledge. The elliptical design naturally focuses and distributes sound across large distances. Spectators seated far from the centre could still hear important announcements and performances. Modern acoustic studies indicate that geometry plays a crucial role in this effect. Whether Roman architects intentionally optimized acoustics or achieved them through accumulated experience remains debated. The same uncertainty surrounds many Roman theatres and public buildings, where acoustic performance often exceeds expectations. What do you think was the most impressive achievement behind LGEM? The massive construction logistics, the underground mechanical systems, or the extraordinary structural engineering that has kept the arena standing for nearly 1,800 years? Carthage, located on the coast of modern Tunisia, overlooking the central Mediterranean, was once the greatest maritime power of the ancient world. Yet more than 2,000 years after its destruction, one question continues to puzzle historians and engineers alike. How did a civilization that left behind so few technical records build one of the most advanced naval and commercial systems of antiquity? The ruins of ancient Carthage are not merely the remains of a lost city. They are the fragments of a technological tradition that disappeared almost completely, leaving behind mysteries that modern archaeology is still struggling to solve. The story of Carthage began in the 9th century BC when Phoenician settlers from Tyre established a colony on the North African coast. Over the following centuries, Carthage expanded into a vast maritime empire controlling trade routes across the western Mediterranean. At its peak during the 3rd century BC, Carthaginian influence extended from North Africa to Spain, Sardinia, Corsica, Sicily, and parts of the Atlantic coast. Ancient writers described a city of enormous wealth, powerful fleets, and sophisticated administration. Then, in 146 BC, after the Third Punic War, Rome destroyed Carthage. The city was burned, much of its infrastructure dismantled, and countless records vanished forever. The modern rediscovery of Carthage began during the 19th century, but systematic excavations accelerated after the 1970s under international archaeological programs supported by UNESCO. Excavations on Bursa Hill, the harbours, residential districts, and surrounding settlements revealed evidence of an urban system far more sophisticated than previously imagined. Yet every discovery seemed to raise new questions. The greatest mystery revolves around Carthage's naval technology. Ancient sources repeatedly describe Carthage as the dominant naval power of the Western Mediterranean. During the First Punic War between 264 and 241 BC, Rome faced a problem. The Romans possessed little naval experience compared with Carthage. According to the Greek historian Polybius, Rome obtained a stranded Carthaginian warship and used it as a template to construct an entirely new fleet. This single event remains one of the most extraordinary episodes in military history. A civilization that would later dominate the Mediterranean effectively copied the ship design of its greatest rival because it could not initially match Carthaginian naval engineering. What makes this mystery remarkable is the speed involved. Ancient sources suggest that Rome built approximately 100 quinqueremes and 20 triremes in a matter of months. Such rapid replication would have been impossible unless Carthaginian vessels were already highly standardized. Archaeologists and naval historians believe Carthage may have employed a form of modular shipbuilding centuries before the concept appeared in modern industry. Components may have been produced in specialized workshops and assembled according to standardized dimensions. However, no complete Punic shipyard has ever been discovered, and no surviving technical manuals explain the process. Evidence from Punic shipwrecks suggests exceptional construction quality. Mortise and tenon joints connected planks with remarkable precision. Hulls were strong enough to survive long-distance voyages and military operations across thousands of kilometers. Some reconstructions indicate that large Carthaginian warships may have exceeded 40 meters in length while carrying hundreds of crew members. The engineering challenge becomes even more impressive when considering that these vessels were built without modern measuring tools, industrial saws, or metal fasteners on the scale used today. Even more mysterious is the infrastructure that supported this naval power. Excavations have revealed the famous military harbour known as the Chthon. Unlike ordinary ports, the military harbour consisted of a circular basin approximately 325 meters in diameter connected to a rectangular commercial harbour. At the centre stood an artificial island that served as a naval headquarters. Archaeological surveys suggest the harbour complex could accommodate roughly 220 warships. This design has a few parallels in the ancient world. Some historians compare it to a modern naval base because of its emphasis on organisation, maintenance, logistics, and rapid deployment. Yet fundamental questions remain unanswered. How did Carthaginian engineers maintain water depth within the harbour? How did they manage sediment accumulation over centuries? What surveying methods allowed such precise geometry? Satellite imagery, underwater archaeology, and sediment analysis have provided clues, but no definitive explanation exists. The harbour appears to have functioned with a level of efficiency that exceeded many contemporary Mediterranean ports. Another technological mystery involves navigation. Carthaginian merchants and explorers sailed far beyond the routes used by most Mediterranean civilizations. The famous voyage of Hanno the Navigator, probably conducted during the 5th century BC, may have reached as far as the Gulf of Guinea along the West African coast. Other expeditions reportedly ventured into the Atlantic Ocean beyond the Strait of Gibraltar. These journeys required navigational knowledge, weather forecasting, astronomical observation, and maritime logistics far beyond what survives in the archaeological record. The disappearance of Carthaginian navigation manuals represents one of history's greatest losses. Unlike Greek and Roman texts, very few Punic documents survive the destruction of the city. As a result, researchers know that Carthaginian sailors crossed enormous distances, but possess only fragments of information about the techniques that made such voyages possible. Some scholars suspect that generations of accumulated maritime knowledge vanished in 146 BC. The city's commercial infrastructure presents another puzzle. Carthage managed one of the largest trade networks of the ancient world. Archaeological evidence reveals the movement of silver from Iberia, agricultural products from North Africa, metals from Sardinia, and luxury goods from across the Mediterranean. Estimates suggest that Carthage controlled trade across millions of square kilometers. Coordinating such a network would have required advanced systems of accounting, taxation, warehousing, and logistics. Yet almost none of the administrative mechanisms survived. Compared with the thousands of surviving clay tablets from Mesopotamia or Egypt, Punic records are extraordinarily scarce. Historians therefore face a paradox. The physical evidence demonstrates the existence of a highly organized economic system, but the documentation explaining how it operated has largely disappeared. The engineering of the city itself raises further questions. Excavations on Bursa Hill revealed carefully planned residential districts, drainage systems, cisterns, and water management infrastructure. Some cistern complexes stored thousands of cubic meters of water. In a region where water security was critical, such systems required advanced understanding of hydraulics, construction techniques, and urban planning. The scale of these installations has led some researchers to compare Carthaginian water management with achievements later associated with Roman engineering. One of the most controversial mysteries concerns the Tophet of Carthage. Thousands of urns containing cremated remains of infants and animals have been discovered in this sanctuary. For more than a century, scholars have debated whether the site represents evidence of child sacrifice or a specialized cemetery for children who died naturally. Modern forensic analysis, isotope studies, and osteological examinations have produced conflicting interpretations. Despite decades of research, no consensus exists. The debate continues to divide experts and remains one of the most contentious issues in Mediterranean archaeology. Perhaps the greatest mystery is not any single structure, harbour, or artifact. It is the disappearance of the knowledge that created them. Carthage constructed fleets capable of challenging Rome, developed one of the most sophisticated harbour systems of antiquity, maintained vast trade networks, and engineered complex urban infrastructure. Yet unlike many ancient civilizations, it left behind remarkably few technical explanations. The destruction of 146 BC effectively erased much of the intellectual foundation behind these achievements. Longshan Temple, standing in the heart of Taipei, Taiwan, is not supposed to be a mystery. Built in 1738 by settlers from Fujian during the Qing dynasty, it is one of the most studied temples in East Asia. Millions of visitors walk through its gates every year. Historians know who built it. Engineers can measure every beam and pillar. Yet the deeper researchers investigate the temple, the more they encounter a disturbing question. How did craftsmen nearly 3 centuries ago create architectural and material technologies that continue to challenge modern understanding? The story begins in Taipei Basin, northern Taiwan. Longshan Temple was established by immigrants from Quanzhou, Fujian, who brought with them centuries of traditional Chinese construction knowledge. Over time, the temple survived earthquakes, typhoons, fires, political upheavals, and even aerial bombing during World War II. In 1945, Allied aircraft bombed parts of Taipei, damaging sections of the temple, yet the main sanctuary survived. Today, despite repeated disasters, the structure remains one of the most important examples of traditional Chinese temple engineering in East Asia. What makes Longshan Temple extraordinary is not merely its beauty. It is the hidden technology embedded within every beam, roof, column, and ornament. The first mystery involves its remarkable resistance to earthquakes. Taiwan sits on the boundary between the Philippine Sea Plate and the Eurasian Plate, making it one of the most seismically active regions on Earth. Modern Taiwan experiences thousands of measurable earthquakes every year. Major earthquakes such as the 1999 Chi-Chi earthquake, which registered magnitude 7.6, demonstrated the devastating power of the island's geology. Yet traditional temple structures built centuries earlier often display resilience that surprises engineers. Unlike modern concrete buildings, Longshan Temple relies primarily on timber framing. The structure functions as a flexible system rather than a rigid one. Instead of resisting seismic energy directly, the building absorbs and redistributes it. Massive wooden columns transfer loads through an intricate network of beams and brackets. During ground movement, these connections can shift slightly without catastrophic failure. Researchers frequently compare such systems to modern seismic isolation technologies. Contemporary skyscrapers often require expensive dampers, tuned mass systems, and computer-designed flexibility mechanisms. Longshan Temple's builders achieved a similar principle using only wood, geometry, and experience. No surviving documents explain precisely how these craftsmen calculated load distribution. There were no structural engineering equations, no computer simulations, and no digital models. Yet, the results continue to perform remarkably well under seismic stress. The second mystery concerns the temple's astonishing joinery system. Thousands of wooden components are connected without relying on modern metal fasteners. Traditional Chinese carpentry employs mortise and tenon joints, allowing pieces to interlock with extraordinary precision. At Longshan Temple, many connections appear almost seamless. Modern architects often compare this system to three-dimensional puzzles. Every component must fit perfectly while simultaneously carrying weight from the massive roof above. A single error can affect the stability of an entire section. Yet craftsmen working with hand tools achieve tolerances that remain impressive even by modern standards. Perhaps most fascinating is the disappearance of the knowledge itself. Many traditional construction techniques were transmitted orally through apprenticeships rather than written manuals. As generations passed, portions of this knowledge gradually vanished. Restoration teams today frequently rely on surviving master craftsmen because historical records alone cannot fully explain the construction process. The third mystery rises above the temple itself. Longshan Temple's roof is among the most recognizable architectural features in Taiwan. The sweeping curves create a silhouette that appears almost impossible. These roofs are not merely decorative. Their shape serves multiple engineering functions simultaneously. Taipei receives approximately 2,400 millimeters of rainfall annually. Typhoons regularly bring intense wind and water. The curved roof channels rain water efficiently away from vulnerable structural elements. At the same time, the design helps distribute loads across supporting columns and beams. Modern wind tunnel testing on traditional East Asian roofs suggests that their geometry may reduce certain aerodynamic stresses. Yet no evidence indicates that 18th century builders possessed formal aerodynamic theories. Through centuries of experimentation, they developed forms that perform surprisingly well under harsh environmental conditions. The fourth, and perhaps greatest mystery, involves the ceramic sculptures covering the roof. Dragons, phoenixes, immortals, warriors, mythical creatures and religious figures stretch across ridges and corners in extraordinary detail. From a distance, these decorations appear artistic. Under closer examination, they become technological enigmas. The rooftop ceramic sculptures endure some of the harshest conditions imaginable. They're exposed continuously to ultraviolet radiation, tropical heat, humidity, acid rain, typhoon-force winds, and sudden temperature changes. Many modern construction materials struggle under such conditions. Yet numerous traditional ceramic elements survive for decades and sometimes centuries. The question is simple: how were they made? Ancient craftsmen possessed no electron microscopes, no spectrometers, and no industrial laboratories. Nevertheless, they developed ceramic recipes capable of producing remarkable durability. The clay had to be carefully selected. Mineral composition mattered enormously. The firing temperature needed precise control. Even small variations could cause cracking, deformation, or rapid deterioration. Studies of traditional Chinese ceramics reveal firing temperatures often exceeding 1000 degrees Celsius. Achieving and maintaining such temperatures consistently required sophisticated kiln management. Fuel selection, airflow control, chamber design, and firing duration all influence the final product. What remains unclear is how craftsmen optimized these variables through experience alone. Modern ceramic engineers rely on extensive laboratory testing to develop durable materials. Historical artisans achieved comparable outcomes using observational knowledge accumulated over generations. Some rooftop dragons contain hundreds of individual components assembled into a single sculpture. The complexity resembles modular engineering systems. Each piece must survive thermal expansion, moisture exposure, and structural movement while maintaining visual integrity. Researchers frequently compare these ceramic traditions to the lost Roman concrete formula. Both represent technologies that worked exceptionally well, yet whose full developmental pathways remain partly hidden. We can analyze the final products, but understanding exactly how ancient craftsmen discovered these solutions remains difficult. The fifth mystery lies in the temple's stone and wood carvings. Longshan Temple contains some of the most elaborate decorative work in Taiwan. Dragons emerge from columns. Layers of figures overlap within impossibly deep reliefs. Flowers, animals, clouds, and mythological scenes intertwine across surfaces. Producing such detail requires extraordinary spatial understanding. Modern workshops often use computer-controlled machinery to achieve comparable complexity. Historical artisans relied entirely on hand tools. The precision becomes even more remarkable when considering the scale. Certain carvings extend across large architectural elements while maintaining consistent proportions. Errors could not simply be erased and restarted. Each cut permanently altered the material. Archaeologists and art historians continue debating how craftsmen organized these projects. Did they use full-scale templates? Did master builders memorize proportions? Were secret measurement systems passed through guild traditions? Definitive answers remain elusive. What do you think is the greatest mystery of Longshan Temple? Its earthquake-resistant wooden structure, its precision joinery, or the ceramic sculptures that have survived centuries of extreme weather? Share your thoughts in the comments below. White Stone Cave, hidden within a rugged limestone landscape, appears at first to be just another ancient cave. Yet beneath its pale stone walls lies a mystery that continues to challenge archaeologists, geologists, and historians. Unlike monumental structures such as Stonehenge or the Great Pyramid, White Stone Cave possesses no towering architecture. Its secrets are carved into darkness itself. Deep inside the cave, traces of human activity reveal evidence of exploration, symbolic behavior, and possibly artistic traditions whose technical foundations remain poorly understood even today. The site first attracted scientific attention when researchers documented signs of ancient human occupation within the cave chambers. Excavations uncovered stone tools, charcoal remains, animal bones, and traces of pigments preserved on protected surfaces. Radiocarbon analysis of associated organic materials suggested repeated human visits spanning thousands of years. While the discovery itself was significant, the deeper mystery emerged when scientists began asking a more difficult question. How did prehistoric people accomplish complex activities in an environment almost completely deprived of natural light. One of the first enigmas concerns navigation. Modern cave explorers rely on powerful LED lighting, digital mapping equipment, laser scanners, and communication systems. Ancient visitors possessed none of these technologies, yet evidence indicates that humans penetrated far beyond the illuminated entrance zones. Some activity areas occur hundreds of meters from daylight. Reaching such locations required precise route knowledge, memory, and planning. Even a minor mistake inside a complex cave system could result in disorientation or death. Researchers studying prehistoric cave use in Europe have noted similar patterns in sites such as Altamira and Lascaux, where people repeatedly reached remote chambers with remarkable consistency. Whitestone Cave raises the same question. How did ancient explorers navigate underground landscapes with such reliability? The challenge becomes even greater when considering illumination. Archaeological evidence from prehistoric caves across Europe demonstrates that ancient people used stone lamps fueled by animal fat, wooden torches, and resin-based lighting systems. Experimental archaeology has shown that a single fat lamp can produce relatively stable illumination for several hours while generating less smoke than a traditional torch. However, operating such systems deep underground required knowledge of fuel management, airflow, and oxygen availability. In enclosed cave environments, smoke accumulation quickly becomes dangerous. Whitestone Cave may preserve evidence that its occupants understood how to exploit natural ventilation patterns within the cave. If true, this would suggest a level of environmental knowledge rarely associated with prehistoric societies. Yet the greatest mystery of Whitestone Cave is neither navigation nor lighting. It is the evidence of ancient artistic activity and the extraordinary durability of the pigments that survived for millennia. Pigments found in ancient caves often appear deceptively simple. To the modern eye, they are merely red, black, yellow, or brown marks on stone. Scientific analysis tells a different story. Studies conducted on prehistoric cave paintings throughout Europe have revealed that ancient artists carefully selected mineral sources rich in iron oxides, manganese oxides, and other naturally occurring compounds. These minerals were then processed into fine powders before being mixed with organic binders such as animal fat, plant extracts, blood, or water. The precision involved in this process is frequently underestimated. Modern laboratory examinations of Paleolithic pigments have demonstrated particle sizes measured in microns. Producing powders this fine requires prolonged grinding and careful preparation. In some cases, pigments were heated to alter their chemical composition and improve color intensity. Experimental studies have shown that heating yellow iron-rich minerals can transform them into deeper red pigments through controlled thermal processes. This raises a remarkable possibility. Ancient artists may have been performing practical chemistry thousands of years before the development of formal scientific theory. Whitestone Cave presents a particularly intriguing example because some pigment traces appear remarkably well preserved, despite exposure to changing environmental conditions over extended periods. Moisture, temperature fluctuations, bacterial activity, and mineral deposition normally degrade organic materials, yet certain ancient pigments can survive for astonishing lengths of time. The famous paintings of Lascaux Cave in France are approximately 17,000 years old. Some paintings in Chauvet Cave exceed 30,000 years in age. Their survival demonstrates an unexpected mastery of material selection. Researchers attempting to understand pigment preservation have discovered that cave microclimates play a critical role. Stable temperatures, limited airflow, and specific humidity conditions can create natural preservation chambers. However, Environmental stability alone does not fully explain the phenomenon. Certain pigments appear to possess exceptional resistance to degradation. Some scientists argue that prehistoric artists deliberately selected minerals not only for visual appearance but also for durability. If this interpretation is correct, it suggests empirical knowledge accumulated through generations of observation and experimentation. The mystery deepens when examining the placement of artistic traces within caves. In many prehistoric sites, images and pigment marks are not distributed randomly. Instead, they appear concentrated in specific chambers and passageways. Studies conducted by acoustic researchers have revealed an unexpected pattern. Locations containing artwork often coincide with areas of unusual acoustic behavior. Echoes, resonance effects, and sound amplification occur more frequently near decorated surfaces than chance alone would predict. This observation has led to a controversial hypothesis. Ancient people may have intentionally selected artistic locations based partly on sound characteristics. If true, Whitestone Cave may represent more than an artistic site. It may have functioned as a carefully chosen ceremonial environment where visual imagery, darkness, and acoustics combine to create powerful sensory experiences. Such behavior would reveal a sophisticated understanding of environmental psychology long before written history. Another unanswered question involves the symbolic meaning of the pigments themselves. Modern science can identify chemical compositions with remarkable precision. Spectroscopy, X-ray fluorescence analysis, and microscopic imaging can determine mineral origins and manufacturing techniques. What these methods cannot reveal is meaning. Why were particular symbols created? Why were specific colors chosen? Were the markings territorial, religious, educational, or ceremonial? The physical evidence survives, but the cultural knowledge behind it has largely disappeared. Comparisons with other prehistoric sites highlight the scale of the mystery. The paintings of Altamira in Spain date to roughly 14,000 years ago. Chauvet Cave preserves artwork exceeding 30,000 years in age. Sulawesi cave art in Indonesia has been dated to more than 45,000 years old. These discoveries demonstrate that symbolic artistic traditions emerged independently across vast geographical regions. Whitestone Cave appears to belong to this broader pattern of human cognitive development, yet many of its technical and cultural foundations remain hidden. Perhaps the most fascinating aspect of Whitestone Cave is that it challenges common assumptions about prehistoric technology. Technology is often imagined as machinery, metalworking, or engineering, yet the creation of durable pigments, the management of underground lighting, the navigation of complex cave systems, and the exploitation of cave acoustics all required specialized knowledge. These achievements depended upon observation, experimentation, and accumulated experience. They represent forms of technology every bit as significant as later architectural innovations. What do you think was the most impressive achievement behind Whitestone Cave? The navigation, the lighting technology, or the creation of pigments that survived for thousands of years? Ptolemais, on the Mediterranean coast of present-day Libya, was one of the largest cities of ancient Cyrenaica. Yet, beneath its streets lies a technological mystery that archaeologists still struggle to explain. A gigantic underground water complex whose full engineering logic remains unknown. The ruins of Ptolemais were first systematically documented by European explorers during the 19th century, while major archaeological investigations expanded throughout the 20th century under Libyan, British, and later Polish missions. What researchers uncovered was not merely another Greco-Roman city. They found evidence of an urban infrastructure system so sophisticated that parts of its operation remain uncertain even after decades of excavation. The greatest mystery of Ptolemais is hidden underground. Beneath the city lies an enormous network of vaulted reservoirs commonly known as the Great Cistern Complex. The structure contains at least 17 interconnected chambers arranged beneath a large area of the ancient city. Estimates suggest the system could store approximately 7,000 cubic meters of water. To put this into perspective, that is enough water to fill nearly 3 Olympic-sized swimming pools. For a city located in a relatively dry region of North Africa, such storage capacity was not simply convenient, it was essential for survival. What makes the complex mysterious is not its size, but its design. Archaeologists can map the chambers, measure the walls, and reconstruct portions of the structure, yet they still debate exactly how the entire system functioned. Water entered through aqueducts and local collection systems, but the precise method used to regulate flow between the chambers remains unclear. Some researchers believe the reservoirs acted as a massive hydraulic regulator, stabilizing water pressure throughout the city. Others argue that the chambers operated as a multi-stage filtration system, designed to remove sediment before water reached public fountains and households. The engineering challenge was enormous. Water moving through interconnected reservoirs must be carefully controlled. Too much pressure can damage structures. Too little pressure can interrupt supply. Modern water engineers solve these problems using mathematical models, pressure gauges, and computerized monitoring systems. The builders of Ptolemais possessed none of these tools, yet they created a system that functioned for centuries. The unanswered question is how they calculated it. No surviving manuals describe the design process. No engineering drawings have been discovered. The physical structure survives, but the knowledge behind it largely vanished. This situation resembles other famous technological mysteries from antiquity. Roman marine concrete continues to puzzle material scientists because of its remarkable durability in seawater. The builders of the Antikythera mechanism created an astronomical computer nearly 2,000 years ago, yet almost no written explanation survived. Ptolemais presents a similar puzzle in the field of hydraulic engineering. The cistern complex becomes even more impressive when viewed in its broader urban context. Ancient Ptolemais covered approximately 280 hectares, making it one of the largest cities in Cyrenaica. Supporting a population of many thousands required a constant water supply for drinking, bathing, industry, sanitation, and agriculture. The city relied on an aqueduct system, extending more than 8 kilometers from inland water sources. Maintaining a stable flow across such distances required precise control of gradients. Modern surveys show that Roman and Hellenistic aqueducts often maintained slopes measured in only a few meters per kilometer. An error of even a small percentage could cause stagnation, overflow, or structural failure. How ancient engineers achieved such accuracy remains a matter of debate. The Greeks and Romans possessed surveying instruments such as the chorobates and groma, but many researchers believe these tools alone cannot fully explain the extraordinary precision seen across major hydraulic systems. Similar questions surround the aqueducts of Rome, the Pont du Gard in France, and the tunnels of Samos in Greece. Ptolemais belongs to this same category of ancient engineering enigmas. Another mystery involves the city's relationship with earthquakes. On July 21st AD 365, one of the most powerful earthquakes in Mediterranean history struck near Crete. Modern geological studies estimate a magnitude exceeding 8.0. The event generated a massive tsunami that devastated coastal settlements across the eastern Mediterranean. Cities such as Alexandria suffered severe destruction. Yet Ptolemais survived and continued functioning as an important regional center. Archaeologists still debate why. Was the city's infrastructure unusually resilient? Did its builders incorporate structural techniques that improved resistance to seismic activity? Were certain foundations specifically adapted to local geological conditions? Excavations reveal multiple phases of reconstruction, but the full explanation remains uncertain. Like many ancient technologies, the practical knowledge may have disappeared while the structures themselves endured. The harbour of Ptolemais presents another unresolved problem. Today, portions of the ancient port lie beneath the Mediterranean Sea. Underwater surveys have identified submerged architectural remains, harbour installations, anchors, and evidence of maritime activity. The existence of these submerged features raises difficult questions. How much of the coastline has changed since antiquity? Did tectonic movements gradually lower parts of the city? Did sea level changes alter the shoreline? Or did the earthquake of AD 365 permanently reshape the harbour environment? Researchers continue using underwater archaeology, sonar mapping, and coastal geology to reconstruct the original harbour layout. However, no consensus has emerged. Understanding the harbour is crucial because maritime trade formed the economic foundation of the city. Without knowing how the port functioned, historians cannot fully explain Ptolemais' rise as a major Mediterranean centre. The city's urban planning introduces yet another technological puzzle. Ptolemais was organised according to a remarkably regular grid system. Streets intersected at carefully planned angles, creating standardised urban blocks. Such layouts are common in Hellenistic cities, influenced by the principles associated with Hippodamus of Miletus, often called the father of urban planning. Yet implementing these designs on a large scale required sophisticated surveying methods. Modern archaeologists can reconstruct city plans using satellite imagery, GPS measurements, drones, and digital mapping software. Ancient surveyors relied on ropes, sighting instruments, geometry, and accumulated experience. Despite these limitations, they achieved results that continue to impress modern engineers. The question is not whether they succeeded. The evidence proves they did. The mystery is exactly how they maintained such consistency across hundreds of hectares without modern technology. Perhaps the most fascinating aspect of Ptolemais is what it reveals about lost knowledge. The city demonstrates mastery of water management, hydraulic engineering, surveying, architecture, logistics, and urban administration. These capabilities were not isolated achievements. They formed part of a complex technological tradition that developed over centuries. Yet much of that tradition vanished. Written records are incomplete. Technical manuals are scarce. The engineers themselves are anonymous. What do you think was the greatest achievement of Ptolemais? The massive underground cistern complex, the long-distance water system, or the engineering knowledge that vanished with the city? Share your thoughts in the comments below. In Mianqi County of Henan Province, China, archaeologists uncovered evidence of a civilization that mastered technologies thousands of years before historians expected them to exist. Long before the rise of Egypt's pyramids, before Stonehenge reached its final form, and nearly 3 millennia before the Shang dynasty produced China's earliest confirmed writing, the people of the Yangshao culture were already building organized settlements, producing sophisticated ceramics, and developing engineering knowledge that remains only partially understood today. The story began in 1921 when Swedish geologist and archaeologist Johan Gunnar Andersson identified unusual prehistoric remains near the village of Yangshao. His discoveries revealed an entirely unknown Neolithic culture that flourished between approximately 5000 and 3000 BC across the middle reaches of the Yellow River. Over the following century, archaeologists uncovered more than 1,000 Yangshao-related sites across northern China. Among them, the Banpo settlement near Xi'an became one of the most famous. What researchers found challenged long-standing assumptions about the technological capabilities of Stone Age societies. The first and perhaps greatest mystery involves pottery technology that appeared astonishingly early. Yangshao pottery ranks among the finest painted ceramics produced anywhere in the world during the Neolithic period. Archaeologists have recovered thousands of vessels decorated with intricate geometric designs, spirals, triangles, fish motifs, human faces, and abstract symbols. Many pieces display remarkable symmetry and consistency. Scientific analysis indicates that numerous vessels were fired at temperatures approaching 900 to 1050 degrees Celsius. Such temperatures may seem ordinary today, but achieving them 6,000 or 7,000 years ago required sophisticated control of airflow, fuel supply, combustion efficiency, and kiln structure. The mystery is that the archaeological record has not fully explained how these temperatures were consistently achieved. In many early farming societies, pottery was fired in open pits or simple kilns that produced uneven results. Yet Yangshao ceramics often exhibit uniform coloration, controlled oxidation, and impressive structural durability. Some vessels survived more than 5 millennia underground, while retaining painted designs that remain visible today. Modern experimental archaeologists have attempted to recreate similar pottery using reconstructed Neolithic techniques, and discovered that maintaining temperatures above 1,000 degrees Celsius requires careful management that resembles a primitive form of engineering rather than simple craftsmanship. Comparisons make the achievement even more remarkable. During parts of the Yangshao period, many regions of Europe still relied primarily on relatively simple pottery traditions. The famous painted ceramics of the Cucuteni Tropilia culture in Eastern Europe emerged roughly during the same broad timeframe, yet Yangshao pottery demonstrates comparable artistic sophistication across an enormous geographic area. Researchers continue debating whether specialized craftsmen existed within Yangshao society and how technical knowledge was transmitted over generations without a writing system. The second mystery concerns settlement planning. The Bampo site, excavated extensively during the 1950s, revealed a community that appeared far more organized than expected for a Neolithic village. Covering approximately 50,000 square meters, the settlement contained residential areas, pottery workshops, storage facilities, and cemeteries arranged according to a recognizable plan. Surrounding the village was a defensive ditch several meters wide and deep. The layout suggests that construction was coordinated rather than random. This raises a difficult question. How did a society without written administration organize large-scale labor projects? Digging thousands of cubic meters of earth, constructing dozens of houses, maintaining communal infrastructure, and coordinating specialized production would have required planning, leadership, and communication systems that remain largely invisible in the archaeological record. The physical evidence demonstrates organization, but the mechanisms behind that organization remain unknown. The third mystery involves symbols that may represent an early form of information storage. Several Yangshao artifacts contain repeated marks, incisions, and painted signs. Some resemble simple geometric symbols, while others appear more deliberate and standardized. These markings have generated decades of debate among archaeologists. Were they ownership marks, clan symbols, religious signs, numerical indicators? Or could they represent a primitive precursor to writing? The importance of this question cannot be overstated. The earliest widely accepted Chinese writing appears on Shang dynasty oracle bones, around 1200 BC. Yet some Yangshao symbols are more than 2,000 years older. Most scholars do not classify them as true writing because they lack sufficient complexity and context. However, their repeated appearance across multiple sites suggests they served a communicative purpose. The exact meaning remains one of the most intriguing unresolved questions in Chinese archaeology. The fourth mystery centers on the transmission of technical knowledge. Yangshao communities occupied vast territories extending across hundreds of thousands of square kilometers. Despite this enormous geographic range, many settlements shared similar pottery styles, construction methods, and cultural traditions. Such consistency implies the existence of communication networks connecting distant communities. The challenge is understanding how those networks functioned. There were no roads in the conventional sense. There were no wheeled transport systems during much of the period. There was no centralized government known to archaeologists. Yet ideas, techniques, and artistic conventions spread across regions separated by mountains, rivers, and great distances. The speed and efficiency with which technological traditions were maintained remain poorly understood. The fifth mystery involves material science. Chemical analyses of Yangshao ceramics reveal that artisans carefully selected specific clay sources. Different mineral compositions produced different firing behaviors. Some clays resisted cracking better than others. Some retained pigments more effectively. This suggests an accumulated body of practical knowledge developed through centuries of experimentation. What makes this mysterious is the apparent precision of that knowledge. Modern material science explains why certain clays perform better under high temperatures. Yangshao potters obviously lacked laboratories, microscopes, and chemical equations. Nevertheless, their choices often produced highly effective results. They understood outcomes without necessarily understanding the scientific principles behind them. The process through which such expertise evolved remains largely speculative. The sixth mystery concerns environmental engineering. Excavations indicate that Yangshao communities were skilled farmers cultivating millet as a primary crop. Agriculture in the Yellow River Basin required adaptation to seasonal flooding, changing river channels, and unpredictable climate conditions. Pollen analysis, sediment studies, and environmental reconstructions suggest that communities successfully managed these challenges for centuries. Yet researchers still debate how they monitored environmental changes. There is evidence of settlement relocation, land use planning, and resource management strategies that imply careful observation of natural systems. Without written records, however, the decision-making processes behind these adaptations remain invisible. Archaeologists can see the results, but not the knowledge system that produced them. Perhaps the greatest mystery of all is why such a technologically capable culture never evolved into an early state comparable to later Chinese civilizations. Yangshao society possessed agriculture, specialized crafts, organized settlements, long-distance exchange networks, and increasingly sophisticated technologies. In many parts of the world, these developments eventually led to urbanization, centralized governments, and monumental architecture. Instead, around 3000 BC, Yangshao culture gradually transformed and gave way to later cultures such as Longshan. The transition remains debated. Some researchers point to climatic shifts. Others suggest population pressures, social changes, economic competition, or technological evolution. No single explanation fully accounts for the transformation. What do you think was the greatest achievement of the Yangshao people? Their advanced pottery technology, their organized settlements, or the knowledge that disappeared thousands of years ago? Share your thoughts in the comments below. Tipasa on Algeria's Mediterranean coast, about 70 kilometers west of Algiers, should not have become one of the Roman Empire's most successful maritime cities. Built on a shoreline exposed to waves, erosion, shifting sediments, and changing sea levels, the city flourished for centuries as a commercial hub connecting North Africa with the wider Mediterranean world. Today, its ruins reveal temples, basilicas, roads, water systems, cemeteries, and harbour structures. Yet the greatest mystery is not what survives. It is how ancient engineers created and maintained a functioning port on a coastline that should have constantly worked against them. The ancient city of Tipasa was originally established as a Phoenician trading post sometime before Roman control of the region. It expanded significantly after the Roman annexation of Mauritania in AD 40 and reached its peak between the 2nd and 4th centuries AD. Modern archaeological investigations began during the 19th century under French researchers, while extensive excavations throughout the 20th century uncovered large portions of the city. In 1982, Tipasa was designated a UNESCO World Heritage Site. Despite more than a century of research, many of its most important engineering secrets remain unsolved. The first and most fascinating mystery concerns the harbour itself. Ancient ports were extremely vulnerable to natural forces. Even modern engineers struggle to maintain navigable harbours without dredging, equipment, satellite monitoring, and hydrodynamic modelling. Coastal sediments transported by waves and currents can gradually fill channels and basins, rendering ports unusable. This process has affected countless ancient harbours across the Mediterranean. The harbour of Ephesus in modern Turkey, for example, was eventually stranded kilometres inland due to sediment accumulation from the Cayster River. Similar problems affected ports in Egypt, Greece, and Italy. Tipasa somehow avoided this fate for centuries. Archaeological evidence suggests that its harbour remained operational throughout much of the Roman period, despite being located on a coastline exposed to complex marine processes. Researchers studying Mediterranean coastal geomorphology have found that even minor changes in current patterns can dramatically alter sediment deposition rates. Yet the harbour's position appears remarkably effective. The obvious question is how ancient engineers selected the site. They possess no sonar systems, bathymetric surveys, aerial photography, or computer simulations. Nevertheless, they identified a location capable of supporting maritime trade for generations. Some scholars believe Roman engineers relied on centuries of accumulated observations from Phoenician sailors and local navigators. Others argue that systematic coastal surveying techniques may have existed that are poorly documented in surviving texts. The mystery deepens because no detailed engineering records from Tipasa have survived. We know the harbour worked, we know ships used it, we know trade flourished. What remains unknown is exactly how its designers predicted long-term coastal stability with such apparent success. The second mystery involves the city's relationship with water. Tipasa was constructed across uneven coastal terrain descending toward the Mediterranean. Such landscapes create serious engineering challenges. Heavy rainfall can generate destructive runoff, while poorly designed drainage systems can undermine foundations and accelerate erosion. Excavations have revealed an extensive network of channels, cisterns, reservoirs, and underground drains distributed throughout the city. Portions of these systems remain visible today. What astonishes researchers is the efficiency of the design. Roman hydraulic engineering is famous throughout the ancient world, yet many details of Tipasa's integrated water network remain unclear. Archaeologists have identified individual components, but reconstructing the complete hydraulic system remains difficult because many sections remain buried or destroyed. Similar challenges exist at sites such as Leptis Magna in Libya and Pompeii in Italy, where surviving infrastructure suggests a level of urban water management far more sophisticated than earlier historians imagined. At Tipasa, engineers successfully balanced freshwater storage, wastewater removal, flood prevention, and urban growth without modern pumps or reinforced concrete. Exactly how all these elements function together remains only partially understood. The third mystery concerns the remarkable durability of the city's construction. Northern Algeria lies within a tectonically active region influenced by the ongoing convergence of the African and Eurasian plates. Historical records document destructive earthquakes throughout the broader Mediterranean basin. Despite this geological reality, substantial portions of Tipasa survived for nearly 2,000 years. Walls, foundations, religious structures and civic buildings continue to stand despite centuries of natural and human disturbances. Modern structural engineers studying Roman architecture have repeatedly discovered techniques that distributed loads more effectively than expected. Certain walls at Tipasa display unusual thicknesses and foundation strategies that may have improved long-term stability. Whether these features were intentionally designed to resist seismic forces remains uncertain. Similar debates surround structures such as the Colosseum in Rome and Roman aqueducts in Spain and France. Ancient builders may not have understood plate tectonics, but they clearly possessed practical knowledge gained through generations of construction experience. The extent of that knowledge remains difficult to measure. Another mystery centers on the materials themselves. Roman concrete has become one of the most studied ancient technologies in the world. Scientific analyses conducted during the 21st century reveal that certain Roman marine concretes become stronger over time through chemical interactions with seawater. Researchers identified minerals such as aluminous tobermorite forming within ancient concrete, contributing to exceptional durability. Modern Portland cement often begins degrading after decades in marine environments, while some Roman structures have survived for nearly 2 millennia. Tipasa presents an intriguing case because its coastal structures endured constant exposure to salt, humidity, and marine conditions. Material analyses indicate the use of local aggregates and regionally available resources. However, researchers still debate whether builders at Tipasa employed modified construction recipes adapted specifically for North African environmental conditions. If they did, much of that technical knowledge disappeared long ago. Like the formula behind Roman marine concrete itself, the precise methods used at Tipasa remain only partially reconstructed through modern laboratory analysis. The city's urban planning introduces another layer of mystery. Viewed from above, the arrangement appears deliberate and highly organized. Roads connect residential districts, religious complexes, commercial zones, cemeteries, and harbor facilities in a coherent pattern that maximizes available terrain. Such planning required accurate surveying, measurement, and long-term vision. Roman surveyors possessed instruments such as the groma and chorobates, but surviving evidence rarely explains how they adapted these tools to challenging coastal landscapes. The precision achieved at Tipasa becomes even more impressive when compared with the limitations of ancient technology. No satellites guided construction. No digital elevation models existed. No geographic information systems processed topographic data. Yet engineers successfully integrated transportation, water management, commerce, and defense into a functioning urban environment. The planning resembles achievements seen at Timgad in Algeria and other major Roman cities, but Tipasa faced the additional complication of an unstable maritime setting. What do you think was the greatest achievement at Tipasa? The harbour engineering, the water management system, or the construction techniques that survived for centuries? Share your thoughts in the comments below. Thousands of crushed sea snail shells scattered across a windswept island off the Atlantic coast of Morocco tell the story of a technology that may never be fully understood. More than 2,600 years ago, Phoenician sailors crossed vast stretches of open ocean to reach this remote outpost, known today as Mogador, where they produced one of the most expensive materials in human history, royal purple dye. Why they chose this isolated island, how they mastered its industries, and how much knowledge has since been lost remains some of the greatest mysteries of the ancient maritime world. The ancient settlement of Mogador was first identified by modern archaeologists during investigations of the island in the early 20th century. Major excavations conducted by French archaeologist André Jodin between the 1950s and 1960s revealed Phoenician pottery, industrial installations, imported goods, and enormous quantities of crushed sea snail shells. These discoveries confirmed that Mogador was occupied by Phoenician traders during the 7th and 6th centuries BC, making it one of the westernmost Phoenician settlements ever discovered along the Atlantic coast. The greatest mystery of Mogador revolves around a technology that even modern scientists struggle to fully reconstruct: the production of Tyrian purple, the most expensive dye of the ancient world. Thousands of fragments of murex shells have been uncovered at the site. These marine snails contain a tiny gland that produces a colourless secretion. Through a complex process involving fermentation, oxidation, sunlight exposure, and chemical reactions, the liquid eventually transforms into an intense purple pigment. The process sounds simple, but the chemistry behind it is extraordinarily difficult. Modern laboratory studies have shown that the dye contains brominated indigo compounds, among the most complex natural pigments used by ancient civilizations. Researchers estimate that producing a single gram of pure Tyrian purple required thousands of murex snails. Some estimates suggest that a single kilogram of dye may have required more than 100,000 shells. The challenge becomes even greater when considering Mogador's location. The island sits on the Atlantic coast, where temperatures, humidity levels, and ocean conditions differ significantly from those of the Eastern Mediterranean, where the dye industry originally developed. Fermentation tanks had to remain within specific temperature ranges. Too much heat could destroy the chemical compounds. Too little heat could prevent the necessary reactions from occurring. Yet the Phoenicians operated this industry successfully on an industrial scale more than 2,600 years ago. No written technical manuals explaining the process have survived. Archaeologists can identify the raw materials and chemical residues, but the precise production methods remain largely unknown. In many ways, the lost knowledge behind Tyrian purple resembles the mystery of Roman concrete. Scientists understand the ingredients, yet many details of large-scale production remain debated. The second mystery concerns navigation. Mogador lies over 4,000 kilometers from the Phoenician homeland in the Levant. To put this distance into perspective, it is comparable to the distance between London and Cairo or between New York and Los Angeles. The Phoenicians reached this destination without magnetic compasses, marine chronometers, radar, or maps resembling those used today. They sailed through the Strait of Gibraltar into the Atlantic Ocean, a body of water far more challenging than the relatively enclosed Mediterranean Sea. Ancient Greek historians described Phoenicians as some of the greatest sailors of antiquity, but exactly how they navigated such enormous distances remains uncertain. They likely used stellar navigation, observing stars such as Polaris and other celestial markers. However, celestial navigation alone cannot explain the remarkable consistency of their voyages. Mogador was not a massive island visible from great distances. Finding it repeatedly required extraordinary geographical knowledge. Some researchers believe Phoenician sailors possessed generations of accumulated observational data concerning winds, currents, seasonal weather patterns, and coastal landmarks. If true, this knowledge represented an advanced navigational science that disappeared long before the modern age. The third mystery involves oceanography. Modern satellite observations reveal that the Atlantic coast of Morocco is strongly influenced by the Canary Current, one of the major eastern boundary currents of the North Atlantic. This current transports vast quantities of water southward and significantly influences marine conditions along the coast. Today, scientists analyze such systems using satellites, ocean buoys, computer simulations, and remote sensing technologies. The Phoenicians had none of these tools, yet their ships consistently reached Mogador and returned safely. This suggests that ancient sailors possessed an empirical understanding of large-scale ocean dynamics. They likely recognized seasonal shifts in currents, prevailing winds, and wave patterns through centuries of observation. The remarkable aspect is not that they understood these forces, but that the knowledge was apparently transmitted with enough accuracy to support regular commercial operations across generations. The disappearance of that accumulated expertise represents one of the greatest intellectual losses of the ancient maritime world. The fourth mystery concerns logistics. Mogador was never a self-sufficient settlement. Fresh water was limited, agricultural land was scarce. Most essential supplies had to be imported. Excavations have revealed pottery originating from Phoenician territories, Carthage, and the Iberian Peninsula. Such evidence demonstrates that Mogador functioned within a highly organized trade network, spanning multiple regions of the ancient world. Maintaining this network required predicting future demand months in advance. Food, water, shipbuilding materials, replacement crews, and trade goods all needed to arrive at the right place and time. Modern shipping companies rely on computers, satellite tracking, weather forecasting, and real-time communications. Phoenician merchants relied entirely on human observation and experience. Despite these limitations, their network operated successfully for centuries. Some historians compare Phoenician maritime logistics to a primitive version of modern global supply chains, remarkable not because of its scale, but because of the absence of advanced technology. The fifth mystery involves shipbuilding. The Atlantic Ocean is considerably harsher than the Mediterranean Sea. Strong swells, unpredictable storms, and powerful currents create conditions that challenge even modern vessels. Nevertheless, Phoenician ships repeatedly crossed these waters carrying fragile cargo, luxury goods, and industrial products. Unfortunately, very few Phoenician shipwrecks have survived. As a result, many details of their naval engineering remain uncertain. Archaeologists know that Phoenician vessels employed sophisticated mortise and tenon joinery, a technique in which wooden planks were locked together using precisely cut joints. This technology produced hulls capable of surviving long-distance voyages. Yet many questions remain unanswered. How effective were their waterproofing systems? How did they manage structural stress during Atlantic crossings? What maintenance procedures allowed ships to remain operational for decades? The lack of surviving vessels means that much of this engineering knowledge has vanished. The final mystery may be the most important of all. Why Mogador? At first glance, the island appears isolated and strategically inconvenient. It lies far from the major urban centers of the Phoenician world. Maintaining a permanent presence there required substantial resources and risk. Yet generation after generation, Phoenician merchants continued returning. One explanation suggests that Mogador served as a gateway to Atlantic trade routes extending toward Western Africa. Another theory proposes that it functioned as a specialized industrial center focused on the production of purple dye and other marine resources. Some researchers believe it may have served both purposes simultaneously. Whatever the answer, the decision to establish Mogador demonstrates a level of geographical awareness that remains astonishing for the 7th century BC. Without satellite imagery, modern cartography, geological surveys, or oceanographic models, ancient sailors identified a location that would become one of the most important Atlantic outposts of the Phoenician world. In northern Tunisia, approximately 50 kilometers south of ancient Carthage, lies the site of Zagouan. It became famous not because of a lost palace, temple, or royal tomb, but because it served as the source of one of the largest hydraulic engineering systems ever built by the Roman Empire. Archaeological investigations conducted during the 19th and 20th centuries revealed that the mountain springs of Zaguin supplied water to Carthage through an aqueduct stretching approximately 132 kilometers. Even today, large sections of the system remain visible, making it one of the longest surviving Roman aqueducts in existence. At first glance, the ruins seem straightforward. Water emerged from mountain springs, entered channels, and flowed toward a city. Yet the more researchers studied the system, the more questions emerged. How did engineers nearly 2,000 years ago construct a gravity-powered water network across mountains, valleys, unstable terrain, and seismic zones without modern surveying equipment? Why does some of the engineering knowledge behind the project appear comparable to techniques that would not be fully replicated until many centuries later? The greatest mystery begins with a simple fact: water naturally flows downhill. For a gravity-fed aqueduct to function, engineers must maintain a carefully controlled gradient throughout the entire route. If the slope becomes too steep, the water gains destructive velocity. If it becomes too shallow, flow slows dramatically or stops entirely. Modern engineers accomplish this task using satellite positioning, laser measurement systems, drones, and computer modeling, but Roman engineers possessed none of these tools. Yet the Zaguin aqueduct maintained a functional gradient across approximately 132 kilometers of highly varied terrain. In some sections, the average slope may have been only a few tens of centimeters per kilometer. To appreciate the difficulty, imagine building a channel from one side of a major metropolitan region to another, while maintaining a nearly perfect downward angle the entire distance. A measurement error of only a few meters accumulated over the route could compromise the system. Roman writers mention instruments such as the chorobates and groma, but surviving descriptions are incomplete. Archaeologists still debate how survey teams achieved such remarkable precision across distances, exceeding those of many modern infrastructure projects. The challenge becomes even more impressive when compared with other famous Roman aqueducts. The Aqua Claudia in Rome stretched approximately 69 kilometers, while the Pont du Gard system in southern France covered around 50 kilometers. Zaguin's network was considerably longer, requiring extraordinary planning and coordination. One of the most fascinating structures at Zaguin is the so-called Water Temple. At first glance, it appears religious. The semicircular facade, columns, niches, and decorative architecture resemble a ceremonial monument dedicated to water deities. Yet, beneath the elegant appearance lies something far more practical. The structure functioned as a sophisticated hydraulic collection facility, where multiple mountain springs converged before entering the aqueduct system. Engineers effectively transformed a natural geological environment into a controlled water processing station. Researchers estimate that the springs could produce thousands of cubic meters of water per day. Before entering the main channel, sediments had to settle and flow rates had to be regulated. This raises an intriguing question. How did Roman engineers identify these specific spring systems as reliable long-term water sources? Modern hydrogeologists use drilling equipment, satellite imagery, groundwater mapping, chemical analysis, and computer simulations, whereas Roman builders relied on observation, experience, and methods that remain only partially understood. The selection proved remarkably successful, as nearly 2,000 years later the springs continue to produce water. The route between Zaguin and Carthage was far from ideal. The aqueduct crossed valleys, hills, changing soil conditions and regions affected by tectonic activity. In several areas, engineers had to construct elevated arcades, carrying the water channel high above the surrounding terrain. Many surviving arches remain standing after nearly 20 centuries, creating another engineering puzzle. How did Roman builders calculate structural loads without modern mathematics, finite element analysis, or reinforced concrete? The tallest surviving sections originally reached heights exceeding 20 meters. Each arch transferred forces through carefully shaped stone blocks, distributing weight into foundations below. The principles involved resemble concepts taught in modern structural engineering, yet the calculations were performed without computers, calculators, or standardized engineering textbooks. Comparisons with other ancient projects make the achievement even more remarkable. The Great Pyramid of Giza demonstrates extraordinary stone placement, while the Parthenon demonstrates advanced architectural precision. The Zaguan system demonstrates something different: large-scale infrastructure engineering operating continuously across an entire landscape. Unlike a temple or monument, an aqueduct had to function every day. One reason sections of the aqueduct survived for so long involves Roman hydraulic concrete. Many channels were lined with waterproof materials known as *opus signinum*. This mixture incorporated crushed ceramics, lime, and other components that created durable, water-resistant surfaces. Modern materials scientists have spent decades studying Roman construction materials because some ancient structures appear unusually resistant to aging. In marine environments, Roman concrete has survived nearly 2 millennia of exposure, while some modern concrete structures require major repairs after only several decades. The exact performance mechanisms remain an active area of scientific research. At Zaguan, waterproof channels successfully transported water over enormous distances while limiting leakage. This required not only advanced material knowledge, but also strict quality control during construction. The mystery is not whether Roman builders understood their materials. The mystery is how they developed such effective formulations through experimentation alone. Transporting water 132 kilometers was only half the challenge. Once the water reached Carthage, it entered one of the largest storage systems in the Roman world. The famous La Malga cisterns could store approximately 50 to 60 million litres of water. Massive vaulted chambers stretched across the site, forming a giant reservoir complex. The scale was extraordinary. An Olympic swimming pool contains roughly 2.5 million litres of water, meaning the La Malga system held the equivalent of around 20 Olympic pools. Yet archaeologists still debate important aspects of the distribution network. Exactly how was water prioritized between households, fountains, baths, workshops, and government facilities? How were seasonal fluctuations managed? How was pressure controlled across different districts? Parts of the network have been identified, but a complete understanding remains elusive. The city consumed enormous quantities of water, yet the operational details behind this urban machine remain partially hidden beneath modern development and centuries of destruction. What do you think was the most impressive achievement of the Zaguan aqueduct? The 132-kilometer survey, the hydraulic engineering, or the lost knowledge behind its construction? Let us know your thoughts in the comments below. A massive walled city near modern Wuhan in Hubei province, China, should not have existed. Around 3,500 years ago, during the Middle Shang dynasty, this urban centre suddenly appeared more than 500 kilometers south of the Shang political heartland, equipped with advanced bronze foundries, large palaces, sophisticated urban planning, and manufacturing technologies rivaling those of the most powerful centres of ancient China. Yet the knowledge that built this city remains one of the greatest technological mysteries of the Bronze Age. The site was first identified in 1954, but its true significance emerged during large-scale excavations beginning in 1974. Archaeologists uncovered a rammed earth city covering roughly 7.5 hectares, surrounded by massive defensive walls and containing elite tombs, palace, foundations, workshops, and extraordinary bronze artifacts. Radiocarbon dating and artifact analysis placed the city between approximately 1500 and 1300 BC, making it one of the earliest major urban centres ever discovered in southern China. What researchers expected to find was a distant Shang outpost. What they found instead was evidence of a technological centre whose capabilities continue to challenge our understanding of ancient engineering. The first mystery is why such an advanced city existed so far from the Shang core. During the 2nd millennium BC, distance was one of the greatest barriers to administration, communication, and technology transfer. The Shang capitals around Zhengzhou and later Anyang were the centers of political and military power, yet Panlongcheng possessed bronze vessels, weapons, ceremonial objects, and architectural techniques nearly identical to those found hundreds of kilometers away in the north. This raises an obvious question. How did such sophisticated knowledge travel across enormous distances in an era without paved roads, large-wheeled transport systems, or centralized communication networks? Archaeologists have proposed that Panlongcheng functioned as a strategic colony established to control the rich copper resources of the Yangtze River basin. However, even this explanation leaves critical questions unanswered. Establishing a distant settlement is one thing. Reproducing an entire technological ecosystem capable of manufacturing high-status bronze objects is another. The transmission of specialized metallurgical knowledge remains difficult to explain. The second mystery is the most astonishing of all: the bronze casting technology itself. Many ancient civilizations mastered bronze production. Mesopotamia, Egypt, and the civilizations of the Eastern Mediterranean all produced impressive bronze tools and weapons. Yet the Shang world developed a manufacturing method unlike almost anything else in the ancient world. Most Bronze Age cultures relied heavily on the lost wax casting technique. In this process, a wax model is covered with clay, heated until the wax melts away, and then filled with molten metal. The Shang craftsmen at Panlongcheng primarily employed an entirely different method known as piece mold casting. At first glance, the difference may seem minor. In reality, it represents one of the most technically demanding manufacturing systems of the ancient world. The process began with a full clay model of the desired object. Craftsmen then created multiple clay mold sections around that model. These sections were carefully removed, fired, and reassembled around a core before molten bronze was poured into the narrow space between them. Every mold section had to align perfectly. A deviation of only a few millimeters could ruin the entire casting. The challenge became even greater because many Shang bronzes featured highly complex decorative patterns known as Taoti masks. These symmetrical motifs covered curved surfaces and contained intricate details impossible to correct after casting. The patterns had to be engineered directly into the molds before the metal was poured. Some ritual vessels discovered at Panlongcheng display all thicknesses of only a few millimeters while maintaining remarkable symmetry. Modern metallurgists studying Shang bronzes have noted that achieving such precision requires extraordinary control over mold preparation, metal composition, pouring temperature, cooling rates, and shrinkage behavior. Bronze typically melts between approximately 950 and 1100 degrees Celsius, depending on composition. Maintaining stable temperatures within this range without modern furnaces, thermometers, or scientific instruments represents a significant engineering challenge. Yet Panlongcheng craftsmen consistently produced objects of exceptional quality. The mystery deepens because archaeologists have never fully reconstructed the complete production chain. Bronze artifacts have been discovered, furnaces have been found, slag and metallurgical debris have been analysed. However, relatively few complete mould systems survive. Researchers can identify portions of the process, but still cannot explain every step that allowed Shang craftsmen to achieve such remarkable consistency. When compared with contemporary civilizations around 1500 BC, the achievement becomes even more extraordinary. Many Egyptian bronze objects of the New Kingdom were smaller and less structurally complex. Bronze production in Mycenaean Greece was advanced, but generally focused on weapons and tools, rather than enormous ritual vessels covered in elaborate cast decorations. Panlongcheng craftsmen were producing large ceremonial objects that required precision engineering on a scale rarely seen elsewhere in the Bronze Age. The third mystery involves the supply chain behind this technological system. Bronze is not a natural material. It requires copper, tin, and often lead. Obtaining these materials demanded extensive mining operations and long-distance transportation networks. Scientific studies of lead isotope signatures indicate that some of the metals used by Shang foundries originated from mineral sources in southern and central China. This suggests that enormous quantities of ore or refined metal traveled through complex exchange networks spanning hundreds of kilometers. The logistics are difficult to comprehend. A single large ritual vessel could require tens of kilograms of bronze. Producing hundreds of such objects over generations would have consumed vast amounts of raw material. Unlike later empires, the Shang lacked extensive canal systems, large draft animals for industrial transport, or advanced road infrastructure. Researchers believe rivers played a crucial role, particularly the Yangtze River and its tributaries. Even so, the scale of material movement required remains one of the least understood aspects of Shang economic organization. The fourth mystery concerns the city's massive rammed earth walls. The walls surrounding Panlongcheng were constructed using layers of compacted earth. This technique, known as rammed earth construction, required workers to deposit soil in thin layers and compress each layer repeatedly using wooden tools. Excavations reveal that some sections of the fortification were more than 20 meters wide. Remarkably, portions of these structures have survived for over 3 millennia despite erosion, flooding, and environmental degradation. Modern geotechnical analysis demonstrates that properly compacted rammed earth can achieve impressive structural stability. However, maintaining consistent density across such massive projects requires careful control of moisture content, soil composition, labor coordination, and construction sequencing. No written manuals survive from the Shang dynasty. As a result, researchers still do not know how builders standardized these processes or trained workers to achieve such consistent results. The fifth mystery involves urban planning. Panlongcheng was not a random settlement. Excavations reveal a carefully organized layout. Palace structures occupied elite zones. Workshops were separated from residential areas. Defensive walls enclosed key administrative spaces. Roads and activity zones appear to follow a deliberate plan. This level of organization suggests sophisticated surveying techniques and centralized management. Yet no measuring instruments from the site clearly explain how engineers established alignments, dimensions, and construction standards. Ancient Egypt, Mesopotamia, and the Indus Valley all developed systems of measurement that supported large-scale construction. Whether the Shang possessed a similarly standardized engineering framework remains uncertain. The final mystery is why Panlongcheng declined. Around the 13th century BC, evidence indicates that large-scale bronze production diminished. Construction activity slowed, population levels decreased. Eventually, the city lost its importance. No evidence points to a catastrophic military destruction. Instead, the decline appears gradual. Some scholars suggest that changing trade routes reduced the city's strategic value. Others point to political shifts within the Shang state. Environmental changes affecting resource access and transportation networks may also have played a role. Yet no single explanation fully accounts for the city's disappearance. Risen ancient city, known in antiquity as Reason, lies on the northern shore of the Bay of Kotor in present-day Montenegro. The ancient settlement occupies one of the most protected natural harbours in the Adriatic Sea, surrounded by steep limestone mountains and deep coastal waters. Archaeological investigations began in the 19th century and expanded significantly during the 20th and 21st centuries, revealing evidence of an important Illyrian and later Roman urban centre. Excavations uncovered defensive walls, residential districts, imported goods, coins, and some of the finest Roman mosaics found in the Balkans. Yet despite decades of research, many of the technologies and engineering systems that allowed Rhizon to become a powerful maritime city remain poorly understood. The greatest mystery of Rhizon begins with geography. The Bay of Kotor stretches nearly 30 kilometers inland and forms one of the most unusual natural harbours in Europe. Surrounded by mountains rising more than 1,500 meters above sea level, the bay resembles a fjord despite being formed through different geological processes. Rhizon occupied one of the safest positions within this protected water system. Ancient sailors faced constant threats from storms, piracy, and unpredictable currents. Most ancient ports relied heavily on artificial breakwaters and harbour engineering, yet Rhizon benefited from natural protection that rivaled some of the greatest naval bases of antiquity. The mystery is not that the harbour existed. The mystery is why the Illyrians selected this exact location centuries before modern hydrographic surveys could measure currents, wave energy, or navigational safety. Modern naval planners analyze countless variables before establishing strategic ports, yet Rhizon appears to have achieved similar advantages more than 2,300 years ago. Archaeologists continue debating whether this was the result of generations of accumulated maritime knowledge, or whether Illyrian navigators possessed a much deeper understanding of coastal geography than historical sources suggest. The harbour's strategic value became so obvious that later Roman authorities maintained and expanded the settlement rather than abandoning it. This continuity suggests that Rhizon occupied one of the most valuable maritime positions anywhere along the eastern Adriatic coast. The Bay of Kotor region receives exceptionally high rainfall, and some nearby mountain areas experience annual precipitation exceeding 4,500 millimeters, among the highest recorded in Europe. For an ancient city, such conditions created enormous challenges. Heavy rainfall increases erosion, destabilizes foundations, damages roads, and complicates urban planning. At the same time, the surrounding karst landscape causes water to disappear underground through limestone formations, making long-term water management extremely difficult. Despite these challenges, Rhizon survived for centuries, raising one of the most fascinating engineering questions associated with the site. How did its inhabitants manage water? Excavations have revealed portions of drainage systems and urban infrastructure, but archaeologists still lack a complete understanding of how the city controlled runoff, protected buildings from flooding, and maintained reliable freshwater supplies. The mystery becomes even more significant when compared with other ancient civilizations. The Romans built aqueducts stretching over 80 kilometers, The Nabateans engineered sophisticated water storage systems at Petra, and the Minoans constructed advanced drainage networks on Crete nearly 4,000 years ago. Yet Rhizon operated successfully within one of the most hydrologically complex environments in the Adriatic. Many researchers suspect that substantial portions of its hydraulic infrastructure remain buried beneath modern construction or unexplored archaeological layers. For centuries, classical authors often portrayed the Illyrians as tribal peoples living beyond the boundaries of major Mediterranean civilizations. Archaeology has gradually destroyed that stereotype. Excavations at Rhizon reveal imported ceramics from Greece, luxury goods from across the Mediterranean, locally minted coinage, monumental architecture, and evidence of extensive commercial activity. The quantity of imported artifacts indicates participation in long-distance trade networks spanning hundreds and possibly thousands of kilometers. This creates another mystery. Where did all this wealth originate? Trade alone may not fully explain the city's prosperity. Some scholars believe Rhizon controlled critical maritime routes connecting the Adriatic with inland Balkan markets, while others suggest it served as a redistribution centre, where goods arriving from the Mediterranean were exchanged for resources from the interior. Yet the precise economic mechanisms remain uncertain. Unlike Rome, Athens, or Carthage, Rhizon left few written records explaining how its economy functioned. As a result, archaeologists can see evidence of wealth, but cannot fully reconstruct the system that generated it. One of the most important discoveries at the site involves coin production. Rhizon minted its own currency during periods of Illyrian rule, a remarkable achievement for a regional power. Ancient coinage represented far more than money. Coins required access to metals, skilled craftsmen, standardized production techniques, political authority, and organized economic systems. The existence of Rhizon's coinage suggests a level of administrative sophistication far beyond what was once attributed to Illyrian societies. Yet mysteries remain. How large was the minting operation? Where did the metal originate? How extensive was the circulation network? Coins linked to Rhizon have been found across parts of the Balkans, indicating influence extending well beyond the city itself. Some researchers compare this phenomenon to other ancient trading powers, whose political influence exceeded their physical size. The evidence suggests Rhizon played a much larger regional role than historians once imagined. Ancient ports rarely functioned through geography alone. Successful maritime centres required warehouses, docks, ship repair facilities, storage yards, administrative buildings, and systems for loading and unloading cargo. Yet, surprisingly little of Rhizon's harbour infrastructure has been identified with certainty. This absence creates one of the site's most intriguing archaeological puzzles. A city engaged in extensive maritime trade should have left behind substantial evidence of commercial facilities, but where are they? Some researchers believe portions of the ancient harbour now lie beneath accumulated sediments. Others suspect rising sea levels, tectonic activity, and centuries of shoreline modification may have altered the original coastal landscape beyond recognition. Modern underwater archaeology has transformed understanding of ancient ports across the Mediterranean, and sites once thought lost have reappeared beneath meters of sediment and seawater. Rhizon may conceal similar discoveries waiting offshore. Perhaps the most overlooked mystery involves knowledge itself. Rhizon's builders selected a defensible location, established successful maritime connections, developed urban infrastructure, managed complex environmental conditions, and participated in international trade. These achievements required expertise in navigation, engineering, logistics, and economics. Yet almost none of the technical manuals, instructions, calculations, or records behind those achievements survive. Do you think the greatest mystery of Rhizon is its lost harbour technology, its unexplained wealth, or the disappearance of Illyrian knowledge? Share your thoughts in the comments below. Wadi Mujib is a vast canyon system in central Jordan, cutting through the Moab Plateau before emptying into the eastern shore of the Dead Sea, the lowest exposed point on Earth at approximately 430 meters below sea level. The canyon stretches for more than 70 kilometers and descends through cliffs reaching nearly 900 meters in height. Archaeological investigations conducted throughout the 20th and 21st centuries reveal traces of ancient roads, fortifications, water systems, agricultural terraces, and settlements dating from the Bronze Age through the Roman and Byzantine periods. Yet the deeper researchers explored the canyon, the more questions emerged about how ancient engineers operated within one of the most hostile landscapes in the Middle East. The greatest technological mystery of Wadi Mujib concerns water management. At first glance, the canyon appears rich in water. Springs emerge from cliffs, streams cut through narrow gorges, and seasonal rainfall feeds the watershed. However, the reality is far more complicated. Rainfall on the Moab Plateau averages only a few hundred millimeters annually, while temperatures regularly exceed 40 degrees Celsius during summer. Worse still, sudden flash floods can transform small streams into destructive torrents within hours. Modern hydrologists consider flash flood prediction one of the most difficult aspects of desert water management. Yet archaeological surveys have uncovered evidence of ancient channels, reservoirs, diversion structures, and agricultural terraces positioned throughout the canyon. The mystery lies in their placement. Many installations occupy locations that appear carefully selected to maximize water capture while minimizing flood damage. Ancient builders somehow identified safe elevations and stable geological zones, despite lacking satellite imagery, computer models, or modern surveying equipment. Researchers estimate that some flash floods in desert canyons can increase water discharge by hundreds of times within a short period. A mistaken placement could have destroyed entire irrigation systems in a single event. How did ancient engineers accurately predict water behavior in such a volatile environment? No written engineering manuals have ever been discovered. Another mystery involves transportation. Wadi Mujib served as a natural barrier separating regions of ancient Moab, yet evidence suggests people crossed and utilized the canyon for centuries. Survey teams have documented remnants of pathways, routes, and access points connecting highland settlements with lower regions near the Dead Sea. This creates an engineering puzzle. Many canyon walls are extremely steep. Some sections consist of nearly vertical sandstone and limestone formations. Even modern hikers often require ropes and specialized equipment to navigate parts of the gorge. Yet ancient communities moved people, livestock, food, building materials, and trade goods through this environment. The challenge becomes even more impressive when compared to other ancient mountain civilizations. The Inca Road network of South America stretched over 40,000 kilometers and required sophisticated engineering to cross difficult terrain. Wadi Mujib presents a similar problem, but within a narrow canyon system vulnerable to erosion and seasonal destruction. Archaeologists still debate exactly how these transportation routes functioned and how frequently they were rebuilt after floods. One of the strangest aspects of Wadi Mujib is how little survives. Historical evidence suggests the canyon occupied a strategic position between the highlands of Moab and trade routes surrounding the Dead Sea. Such a location should have supported observation posts, defensive structures, storage facilities, and transportation infrastructure. Yet the archaeological record remains surprisingly incomplete. Researchers believe repeated flooding, landslides, and sediment deposition may have buried or destroyed large portions of the ancient landscape. Modern geological studies show that canyon environments can accumulate meters of sediment over centuries. Entire structures can disappear beneath alluvial deposits without leaving visible traces. This raises a fascinating possibility. Could significant portions of Wadi Mujib's ancient infrastructure still remain hidden beneath layers of rock and sediment? Ground-penetrating radar has transformed archaeological discoveries elsewhere, revealing buried cities and structures invisible from the surface. However, the steep terrain of Wadi Mujib makes large-scale investigation extremely difficult. The true extent of ancient occupation may remain unknown. The canyon presents another technological mystery that receives little attention. Flash floods remain one of the greatest natural dangers in Wadi Mujib today. Modern warning systems, weather forecasting, and hydrological monitoring help reduce risk, yet floods still pose serious threats. Ancient inhabitants possessed none of these technologies. Nevertheless, many surviving archaeological features appear positioned with remarkable awareness of flood behavior. Terraces often occupy elevated zones. Structures tend to avoid the most dangerous channels. Water control features frequently appear located where natural geology offers protection. This suggests generations of accumulated environmental knowledge. Ancient engineers may have developed an understanding of watershed behavior through long-term observation. They may have recognized patterns invisible to outsiders. The mystery is that this knowledge was never formally recorded. The expertise disappeared while only the physical results survived. The Dead Sea region was one of antiquity's most valuable economic zones. Ancient peoples extracted salt, bitumen, minerals, and other resources from surrounding areas. Bitumen alone was highly prized throughout the ancient Near East for waterproofing, construction, and industrial purposes. Transporting these materials through Wadi Mujib would have been enormously challenging. The canyon contained steep descents, narrow passages, unstable slopes, and seasonal flood zones. Even moving relatively small quantities of goods would have required organization and planning. Yet evidence suggests regional trade networks operated successfully for centuries. How were heavy loads moved through such terrain? Did ancient communities use animal caravans, specialized paths, rope systems, or techniques that left little archaeological evidence? No definitive answer exists. The logistical solutions that supported commerce in the canyon remain largely unknown. Perhaps the most overlooked mystery concerns geology. Many surviving archaeological features in Wadi Mujib appear associated with relatively stable rock formations. This is significant because the canyon cuts through multiple geological layers, including limestone, sandstone, marl, and other sedimentary deposits. Some formations resist erosion far better than others. Modern engineers evaluate slope stability through geotechnical surveys, drilling programs, and computer modeling. Ancient builders relied entirely on observation, yet they repeatedly selected locations that survived for centuries. This pattern resembles other remarkable achievements of the ancient world. The Nabateans at Petra understood which cliffs could safely support monumental facades. Roman engineers selected stable foundations for aqueducts spanning vast distances. In Wadi Mujib, ancient builders may have possessed a similarly sophisticated practical understanding of geological behavior. The methods they used have vanished. Wadi Mujib occupied an important position within a broader historical landscape. The canyon lies near regions associated with the ancient kingdom of Moab, biblical traditions, Nabatean trade networks, Roman administration, and Byzantine settlement systems. For thousands of years, people adapted to one of the most difficult environments in the region. The archaeological evidence reveals engineering solutions, transportation systems, water management strategies, and environmental knowledge far beyond what many would expect from communities living in a desert canyon. Yet almost none of the technical explanations survive. Unlike Roman engineering texts or later architectural manuals, Wadi Mujib left behind very few written records explaining how its infrastructure functioned. Researchers can study the remains. They can map the terrain with drones, analyze sediments with laboratory equipment, and reconstruct ancient landscapes using digital models. But the reasoning behind many decisions remains hidden. What do you think is the greatest mystery of Wadi Mujib? The lost water engineering, the vanished transportation network, or the ancient knowledge of flash floods? Share your thoughts in the comments below. More than 5,000 years ago, while much of the world was still organized into small farming communities, a mysterious culture in what is now northeastern China built ceremonial complexes, massive stone tombs, sophisticated religious structures, and some of the most advanced jade artifacts ever discovered from the Neolithic age. Today, the archaeological site of Nihiliang continues to challenge traditional ideas about the origins of Chinese civilization and raises questions about technologies that appear far ahead of their time. The modern story of Nihiliang began in 1981 when archaeologists conducting surveys in Liaoning province identified unusual stone structures scattered across a mountainous region. Large-scale excavations led by researchers from the Liaoning Provincial Institute of Cultural Relics and Archaeology soon revealed something extraordinary. The site belonged to the Hongshan culture, a Neolithic civilization that flourished between approximately 4,700 and 2,900 BC. What emerged from the ground was not a simple settlement, but a vast ceremonial landscape covering nearly 50 square kilometers, containing altars, temples, elite tombs, stone platforms, and ritual structures unlike anything previously known from prehistoric China. The first mystery involves the sheer scale of planning behind Nihiliang. The ceremonial complex stretches across ridges and hilltops, separated by considerable distances. Archaeologists identified more than a dozen major ceremonial locations, arranged across difficult terrain. Creating such a landscape required surveying, planning, and coordination on a level normally associated with later civilizations. Yet the builders possessed neither metal tools nor written records. Modern engineers rely on maps, mathematical calculations, and precision instruments to coordinate large construction projects. The people of Hongshan apparently achieved similar organizational results over 5,000 years ago, using methods that remain largely unknown. Some researchers compare this achievement to the planning visible at Göbekli Tepe in Turkey, which dates to around 9,600 BC. But Nihiliang demonstrates an even larger integration of ritual architecture across a regional landscape. One of the most famous discoveries at the site is the so-called Goddess Temple. Excavations uncovered the remains of a large ritual building containing clay sculptures of human figures. Among them was a striking female face with eyes inlaid with jade. The sculpture was significantly larger than life-size and represented one of the earliest monumental religious images ever found in East Asia. The mystery lies in how such statues were produced. Clay shrinks during drying and firing, making large sculptures vulnerable to cracking and collapse. Modern ceramic artists carefully control moisture, temperature, and firing conditions to prevent structural failure. Yet the builders of Nihiliang successfully created large ritual figures thousands of years before the development of advanced kilns. Archaeologists still debate the firing techniques used and how temperatures were controlled with sufficient precision to produce durable monumental sculptures. The second mystery centers on the massive stone tombs scattered throughout the ceremonial zone. Some tombs contain carefully arranged stone chambers constructed from large slabs weighing several tons. These stones were transported, positioned, and assembled with remarkable stability. Unlike later civilizations, the Hongshan people had no evidence of wheeled transport, iron tools, or large draft animals. Moving multi-ton stones across rugged mountain terrain would have required sophisticated engineering solutions. Experimental archaeology suggests that transporting even a 2-ton block using wooden rollers and human labor demands substantial organization. Some of the Nihiliang stones exceed those weights considerably. The exact transportation methods remain uncertain, leading some researchers to describe the site as one of the most impressive examples of prehistoric construction in East Asia. The third mystery concerns the unusual pyramid-like structure discovered within the ceremonial complex. Built from layers of stone and earth, the structure rises roughly 16 meters above the surrounding terrain. Although smaller than the pyramids of Egypt, it demonstrates a similar concept of monumental artificial elevation. Geological studies indicate that thousands of cubic meters of material were deliberately transported and deposited. Constructing such a platform required not only labor, but also long-term planning and social control. Archaeologists estimate that projects of this scale would have demanded coordinated efforts involving hundreds or possibly thousands of workers. Yet no large urban center has been found nearby. This creates an intriguing paradox. How did a society apparently lacking cities mobilize enough labor to create monumental ceremonial architecture on this scale? The fourth and perhaps greatest mystery involves jade technology. Among all discoveries at Nihiliang, none astonish researchers more than the extraordinary jade artifacts buried within elite tombs. The Hongshan culture produced intricate ceremonial objects including dragons, birds, rings, masks, and abstract ritual forms. The most famous is the C-shaped jade dragon, often called one of the earliest dragon representations in Chinese history. From a technological perspective, these objects appear almost impossible. Jade, particularly nephrite, possesses a hardness of approximately 6 to 6.5 on the Mohs scale. This makes it harder than steel used in many ancient civilizations and significantly more difficult to shape than common stone. Unlike softer materials, jade cannot simply be carved with a sharp blade. It must be ground, drilled, polished, and shaped through abrasion, a process that is extraordinarily time-consuming. Microscopic studies conducted on Hongshan jade artifacts reveal highly regular surfaces, precise drilled holes, smooth curves, and remarkable symmetry. Some perforations measure only a few millimeters in diameter, while extending deep into the material. Modern researchers believe abrasive compounds such as quartz sand may have been used together with cord drills or tubular drilling devices. However, reproducing some of these artifacts experimentally requires hundreds of hours of labor even with modern knowledge of ancient techniques. The mystery becomes even deeper when examining standardization. Many jade objects discovered across different Hongshan sites display consistent proportions and manufacturing styles. This suggests specialized craftsmen working according to established technical traditions. Yet no workshops have been conclusively identified that explain how such expertise was transmitted. Unlike Egypt or Mesopotamia, where written records preserve aspects of craft production, the Hongshan culture left no known writing system. The knowledge behind these masterpieces vanished almost completely. Comparisons with other ancient civilizations only emphasize the puzzle. In Mesopotamia around 3500 BC, complex societies were developing writing systems but produced relatively limited jade craftsmanship. In pre-dynastic Egypt, monumental architecture was emerging, yet jade working remained less sophisticated. At Nihiliang, A society without cities, writing, or metal industries achieved a level of jade processing that continues to impress specialists today. Some archaeologists describe Hongshan jade production as one of the greatest technological achievements of the Neolithic world. The fifth mystery concerns religion and social organization. New Heliang contains evidence of elaborate ceremonial activity, including altars, ritual platforms, temples, and elite burials. The scale of investment suggests a highly organized belief system capable of mobilizing large populations. Yet researchers still cannot determine whether Hongshan society functioned as a chiefdom, an early state, or an entirely different form of social organization. The ceremonial complex appears to have served as a regional religious center, attracting communities from vast distances. Such integration required communication networks and political structures that remain poorly understood. Another unresolved question involves the sudden decline of the Hongshan culture. Around 3000 BC, many major Hongshan centers were abandoned. Some climate studies suggest environmental changes reduced agricultural productivity. Others point to social transformation, migration, or economic disruption. None of these explanations fully account for the disappearance of a culture capable of such remarkable achievements. The ceremonial centers fell silent, the temples collapsed, and the knowledge that produced some of the world's finest Neolithic jade artifacts faded into history. Erlitou is one of the most mysterious archaeological sites ever discovered in East Asia. Situated near modern-day Yanxi in Henan Province, China, it dates to approximately 1750–1530 BC and emerged during a period when Chinese civilization was supposedly transitioning from legend into recorded history. Yet, Erlitou presents a paradox. Archaeologists have uncovered evidence of a highly organized urban center, monumental palaces, sophisticated bronze workshops, and large-scale craft industries that appear centuries ahead of what many experts once believed possible. Even today, more than 60 years after its discovery, fundamental questions remain unanswered. Who built Erlitou? Was it the capital of the legendary Xia dynasty? And perhaps most importantly, where did its remarkable technological knowledge originate? The modern story of Erlitou began in 1959 when archaeologist Xu Xusheng conducted surveys in the Yiluo River basin while searching for evidence connected to ancient Chinese historical records. Excavations soon revealed an enormous settlement covering roughly 300 hectares. What initially appeared to be another Bronze Age village quickly proved to be something far more significant. Beneath the soil lay the remains of palatial complexes, carefully planned roads, industrial districts, and elite residential zones. Radiocarbon dating later placed the city in the early Bronze Age, making it one of the earliest known state-level centers in China. The first mystery is the sudden appearance of urban planning. Many ancient cities evolve gradually over centuries. Erlitou appears different. Archaeologists discovered a carefully organized layout featuring broad roads, ceremonial spaces, palace compounds, and specialized production districts. The largest roads measured more than 20 meters wide, an extraordinary scale for the period. Palace Zone 1 alone covered approximately 100,000 square meters. Such planning required centralized authority, engineering knowledge, and labor management on a scale rarely seen elsewhere in East Asia at the time. What makes this particularly puzzling is that no earlier settlement in the Central Plains demonstrates the same level of organization. The transition appears surprisingly rapid. It is almost as if a fully developed governing system suddenly emerged. Comparable developments occurred in Mesopotamia around Ur and Uruk, or in Egypt during the formation of the Old Kingdom. Yet Early 2 developed independently thousands of kilometers away. How such a complex administrative system appeared remains one of the site's greatest mysteries. The second mystery involves bronze technology. Early 2 produced some of the earliest large-scale bronze artifacts in Chinese history. Excavations uncovered bronze ritual vessels, bells, weapons, tools, and decorative objects. More importantly, archaeologists discovered extensive foundries capable of mass production. The technology used was remarkably advanced. Early 2 craftsmen employed piece mold casting, a technique requiring multiple precisely manufactured clay molds assembled around a central core. Unlike simple open mold casting seen elsewhere, piece mold casting demanded careful planning, standardized measurements, temperature control, and extensive metallurgical expertise. Modern experiments show that successful bronze casting requires temperatures exceeding 1,000 degrees Celsius. Maintaining such conditions consistently without modern equipment represents a major engineering achievement. Some researchers compare Early 2's bronze industry to the early bronze workshops of Mesopotamia. Yet the Chinese system evolved along an entirely different technological path. The origins of this knowledge remain unclear. No transitional phase has been identified that fully explains how Early Tao craftsmen achieved such sophistication. The third mystery centers on the palace foundations themselves. Archaeologists uncovered multiple large palatial structures built using rammed earth technology. Palace 1 measured approximately 108 meters long and 100 meters wide, covering nearly 9,600 square meters. For comparison, this area exceeds the footprint of many later royal compounds. Rammed earth construction involves compressing layers of soil until they form an extremely dense and durable structure. Modern engineering tests have demonstrated that properly compacted rammed earth can achieve impressive compressive strength. The foundations at Early 2 survived for more than 3,500 years despite earthquakes, floods, and environmental erosion. The mystery lies in the precision. The builders maintained remarkably straight alignments and geometric consistency across large distances. Yet no measuring instruments, architectural manuals, or engineering records have survived. The existence of such accurate planning suggests professional surveyors and architects whose identities and methods have been completely lost. The fourth mystery, and perhaps the most astonishing of all, involves Early 2's vast jade and gemstone production network. While bronze often attracts the most attention, the jade industry may reveal even more about the technological capabilities of this civilization. Archaeologists have recovered hundreds of jade artifacts, turquoise inlays, ceremonial objects, ornaments, and ritual items from elite burials and palace areas. These materials did not originate locally. Geological studies indicate that some jade likely came from deposits located hundreds of kilometers away. Turquoise sources may have been even farther. This means Early 2 maintained long-distance procurement networks capable of transporting valuable raw materials across large regions. The scale alone is extraordinary. Acquiring jade is only the beginning. Jade ranks between 6 and 7 on the Mohs hardness scale, making it extremely difficult to shape. Unlike softer stones, jade cannot simply be carved with ordinary tools. It must be slowly ground, drilled, polished, and shaped using abrasive materials. Microscopic analysis of Early 2 jade objects reveals evidence of advanced manufacturing techniques. Researchers have identified signs of rotary drilling, abrasive cutting, precision polishing, and highly standardized finishing methods. Some perforations measure only a few millimeters in diameter, yet extend through thick pieces of jade with remarkable accuracy. Even modern artisans require specialized equipment to reproduce similar results efficiently. One famous example is the turquoise dragon discovered at the site. Measuring approximately 70 centimeters in length, the artifact consists of more than 2,000 individual turquoise fragments carefully arranged into a complex dragon-shaped mosaic. Every fragment had to be cut, shaped, positioned, and secured with extraordinary precision. The level of craftsmanship rivals some of the finest decorative works produced anywhere in the Bronze Age world. The mystery is not simply how the objects were made, it is how an entire production system operated. Specialized miners had to obtain raw materials. Traders transported them across vast distances. Craftsmen processed the stones. Supervisors maintained quality standards. Elite patrons commissioned and distributed finished products. Such a network implies an administrative structure of surprising complexity. Comparisons with other civilizations make the achievement even more remarkable. Ancient Egypt imported turquoise from Sinai and lapis lazuli from Afghanistan, while Mesopotamian cities traded for precious stones across Western Asia. Erlitou appears to have developed a similarly sophisticated resource network independently. Yet, unlike Egypt and Mesopotamia, written records explaining the organization of these activities have never been found. The fifth mystery concerns political power. Erlitou displays nearly every characteristic associated with an early state. Archaeologists have identified social hierarchy, specialized industries, centralized planning, elite residences, ceremonial architecture, and controlled production zones. Yet direct evidence of writing remains extremely limited. This creates a puzzling contradiction. How did administrators coordinate labor, taxation, resource distribution, and construction projects without a mature writing system? Some scholars argue that perishable records may have existed on bamboo, wood, or textiles that failed to survive. Others suggest alternative administrative methods involving oral traditions and symbolic systems. Regardless of the explanation, the absence of clear records leaves many questions unanswered. The sixth and ultimate mystery is whether Erlitou was the capital of the legendary Xia dynasty. Ancient texts such as the Book of Documents and later historical works describe the Xia as China's first dynasty. According to tradition, it ruled before the Shang dynasty. However, no contemporary inscriptions have ever confirmed its existence. Chronologically, Erlitou fits the expected timeframe remarkably well. Its rise coincides closely with estimates for the late Xia period proposed by many historians. Its scale, wealth, and political organization also match descriptions of an early dynastic center. Yet no artifact discovered at Erlitou explicitly mentions the Xia dynasty. This leaves researchers divided. Some believe Erlitou represents the archaeological reality behind the Xia legends. Others argue that the connection remains unproven. More than half a century of excavation has not resolved the debate. If Erlitou was not the Xia dynasty, then who built this extraordinary city? Share your thoughts in the comments below.